but now since he's a speaker, Gerald, could you maybe? Yes. Sorry, yeah, for not giving you a heads up. So anyway, so let's open the first session. Our first speaker is Peter Binev, and he will be talking about solving PDEs with incomplete information. Peter, please.
Okay, so
this is the laser pointer, right?
This is the laser
forward and backward.
I have to use that. Okay, I'll go downstairs because, yeah, it's more comfortable from here. I want to talk about the problem which is kind of motivated from what people name physics-informed learning or something like this. And that motivated us to do this research, which is published in Sinum last year. This is the list of my co-authors, which contributed to this research, and I want to talk a little bit about this. So we often, when we are talking about physics-informed learning, we have some PDE in mind in which we don't have complete information about it. And this incompleteness could come from different sources. So that's why we wanted to consider a very simple problem in which we're missing some information about the PDE, and we want to use data actually to find out how well we can approximate the solution. And we want to actually do the neo-optimal numerical algorithm to approximate U. So I'll formulate the problem more precisely. We consider the Laplace problem because it's very easy. So we assume that we're given the omega, we're given its boundary, and then, as usual, for this equation, we assume that the right-hand side is in h-1 and the boundary values in h1 half. That motivates the use of h1 norm for measuring the error of the solution. And in order to have the incomplete information, we assume that, we have complete information of f, however, we don't know g. Of course, if we have absolutely no information about g, it's impossible to solve anything. So what we assume is that g belongs to a known compact set in h1 half on gamma, and this is our knowledge about this boundary data. So what we do, so we have this equation, we assume that we have this compact set K, which actually gives us all the possible solutions for some G which is in that compact class on the boundary. So when we have that, now we want to the help of some data observations, and for these data observations, again, we to have the full mathematical analysis, we need to know something, and we assume that we know the linear functionals, which describe these measurements. Of course, so we assume that the data is the vector W of all the data points of, as I said, known linear functionals. So based on that, we can define a set K W, which actually is the set K of solutions, but with the additional condition that they satisfy the data exactly. So when we have that, we can formulate our problem. So the problem is to find a solution U hat, which approximated simultaneously all the U in this compact set KW. So that is the classical approximation theory problem. So for this problem, we define a Chebyshev ball, which is the smallest ball in the H1. This is the space in which we measure distances. And the small ball that contains the KW. And then the Chebyshev radius is actually telling us what is the maximal possible error in this approximation, and the Chebyshev center is what is the solution practically on the problem. So we have these quantities, and we can define what is the near optimal recovery. The near optimal recovery, this is the maximal possible error to be less than constant times the radius. The radius is the best possible approximation. So what is the problem there? The problem is that when we do the approximation, we usually have some quantity epsilon, which describes our error of approximation. And then we want this epsilon practically to be comparable with the radius. If it is not, then it will not be a good solution. So in our research, actually, we want to have the full mathematical derivation how we can approximate the epsilon so we can claim this near optimal recovery. Okay, so the reason we choose this equation is actually we have a full mathematical knowledge of what is going on, and we want also to use the finite element methods because also we have a full theory about it. So what we have in mind, though, is that we can consider several different problems, and we can recover with deep neural networks or something like this, but then the mathematical theory should be built in a similar manner. So what we want to put ahead is some framework on how these problems should be resolved mathematically. So in this case, as I said, we have a very comfortable thing because then we can consider U0 to solve the Laplacian equation with zero boundary conditions, subtract it from the actual solution U, and then we will receive some harmonic function. So practically, we want to reduce that to solving the problem for harmonic functions and see what will happen. So when solving the problem with harmonic functions, so we want to define a functional class, so for which so we have this smoothness index S, which corresponds to the smoothness index on the boundary. So that means it was H1/2, so S, we'll assume it's bigger than H1/2. When defining and by definition, it is simply what is the HS error on the boundary of the function V. So in that, what is good about this is that it's a Hilbert space, which is compactly embedded in H1, and we practically, because of that, we have some constant CS, which actually express this embedding in terms of the norms. So when we have the H1 norm of V, we can estimate it with the norm in this harmonic space, HS. Okay, so how the recovery of the harmonic function works? So first of all, we have to solve this equation for U0. So when we solve it, because we have the linear functionals, LU would be a sum of lambda U would be a sum of lambda U0 and lambda of UH. And practically, we'll have the information W prime about the values of the functionals at this UH function, which is just the difference between W and lambda U0. So, and that means that now we can reformulate the problem, and the radius in that ball would be the radius of the Chebyshev ball would be similar to the radius of the same as the radius Chebyshev ball of this function with information kw, and h means that it is in the space of harmonic functions. So what is important here is that U0 must be computed, which means that we will have an approximation of it. And when you have this approximation U0 hat, that means we will not have exact values of these functionals. So that means when we reformulate for the harmonic functions, we'll have the optimal recovery, but with perturbed observations, W prime. So we have to take care of that in estimation of the error, which is one of the hurdles usually people have in these cases. So we want to recover this component from the given data and want to solve first this problem, and then we have something very comfortable when we have the Hilbert space, because we have this minimal norm interpolant property, which means the following: when we have a Hilbert space and measure the norm in some general Banach space, that might not be H1, that could be some other space here. We only need that H should be continuously embedded in the space X. And then if we're interested in the optimal recovery of a function, which is in the unit ball of UH, then we, however, we measure this optimal recovery in terms of the norm in X. Then we have the general property that this is minimal norm interpolant. This is the minimum based on approximation in the norm in H. And when we have this function, this would be the center of our Chebyshev ball. So that will solve the problem. However, the radius would be different, and this would be based on Rx. I have to mention that even if we don't have this property, it is still possible to solve the problem eventually with larger constant. Say, if we have in the setup that we don't have a Hilbert space, but a general Banach space, and then we measure the norm in another Banach space, then the minimal norm interpolant, of course, will not be true. However, if we are able to recover any point from the ball, which we have, so any point, then we'll have a neo-optimal recovery with constant 2. Why? Because of the triangle inequality, we'll have that. But let me mention that when we do the approximation, we will always be outside of this ball. So in a sense, that's why it's a very good problem which we're solving, because we are considering approximation of harmonic functions, and the results we receive are not harmonic functions. That means they're outside of the ball. We commit some error, and we have to have the full knowledge of this error. So that means we have to control the error all the time. Okay, so first of all, something technical, which unfortunately, when people write books, they write very nice things. However, usually they don't write what we need in writing papers, so we have to actually make some short proofs of very well-known results which we couldn't find anywhere in the books. But as I said, these are well-known results. So first of all, when we want to have a norm, we can consider it of the G, so that means on the gamma, we can consider two different formulations. One is to use the trace norm generated by the norm of the function on the whole domain. And we can use an intrinsic norm using different types of definitions of which actually define it as a function only on the curve, on the gamma, on the boundary. So in this case, sorry, in this case, there are several different considerations to be done, and practically it turns out that when the boundary is not very smooth, we cannot claim much, and we have to restrict ourselves to S. Keep in mind that S should be bigger than 1/2 because of the way the problem works. We have to have that this space should be continuously embedded in H1, so that means the index should be bigger than 1. But at the same time, we cannot claim much the equivalence of the intrinsic norm and the trace norm if we don't, we have very large S. So the consideration should be done up to S equals 3/2. We consider 2 and 3 dimensions, so for high dimensions it's different. So what is the thing? So the thing is when we have a smooth, so we have some smoothness. So if we have smoothness S could be a very large number, we have some restriction of the possible space of functions HR. And these restrictions come from the properties of the boundary. If it is a smooth one, R star could be infinity. However, if we only know that the domain is convex, then R star should be at most 2. That is the case we considered to test 3/2 on the previous slide. However, if it is non-convex polygonal domain, then we have further restrictions, and particularly 2D for the polygons, it is well known what is the property. So we now consider the linear functionals. So what we have to know about the linear functionals, the first way, if these are continuous linear functionals in H1, that would be the most comfortable thing. And in this case, we want to have the Ritz representers. We consider them in the HS, the harmonic spaces. And then, of course, we want them to be linearly independent. And if they are linearly independent, then their Ritz representers would be also linearly independent. And we can put that the Gramian matrix is invertible. So the Gramian matrix is defined in the usual way, and what we have, so when we define it, we could consider, okay, how we calculate the W prime. This is the data from which we subtract the results in our approximation. It is still considered that this is the exact solution here, and then theoretically we can say, okay, based on this calculation of W prime, we can consider the linear system with the Gramian matrix times some unknown constants A star to be equal to W prime, and then we can define the harmonic solution as a linear combination of these Ritz representers of the functionals. So that is one way of doing that, and this is what would be our tool for calculations. So how to calculate the minimal norm interpolant? We first of all we have to have this difference, so that should be inside of the radius. If we calculate them, that actually is the UH star, which was defined on the previous slide, is the minimal norm interpolant, and then for it we have that we're within our Chebyshev radius. So when we have the recovery error, then we can, if we have that, because we just add to this solution U0 in order to receive the U to UH, and of course we'll receive the approximate solution, not actually the approximate, but the actual solution U star, and we'll have the same, the claim of the best possible error. So now we come to the problems. The problem is that you cannot recover exactly U star. You can recover some function U hat of H1, which just approximates U star. And then we'll have some epsilon, which is the bound of all U's, and then we'll have this recovery, we'll have this, the radius plus epsilon, and now we have to try to evaluate what the epsilon is, and that is the purpose of our investigation, how we can bound the epsilon based on the information we know. So that is this some technical slides. So the numerical recovery. First of all, we assume that lambda are linear functionals, which we know, and they have a general. So their norms is smaller than lambda. For each of the functional, there is some general lambda, which is the maximum of their norms. So that would be one thing. And then the other thing is to decide how to measure the data vectors. So the data vector, we don't use exactly the L2 norm. We use a weighted norm in which we divide actually by 1 over m to have the average error at each data site. So, and then in this case, we can write that the norm of lambda as a vector of linear functional is less or equal to this capital lambda times the norm of V in H1. So that means, I emphasize again, because we'll see a little bit later that we might not want lambdas to be continuous functionals in H1, and then we have to do something else in that case. What is our recovery algorithm? It's based on 4 steps, which I talk more or less about them. The first one is to find the approximation of the zero boundary condition function. So if we find such an approximation, we want it to satisfy some inequality with some quantity epsilon 1, which we will define. So practically, in the next step, we'll define the epsilon 2, and we want them to have such values that if we have prescribed accuracy epsilon, we want to achieve it. So we want to find how big can be epsilon 1, because in general, if we approximate U0, you can do it with any accuracy we want, but we have to know which is it in order to have optimal complexity of the algorithm. And then after we calculate this, we can calculate the approximate value of W prime. And because we have this general estimates with the lambda, we have this lambda s, which is simply this constant, embedding constant Cs times lambda. And we can claim in general that we have some estimate of the error, which is of this type, lambda times epsilon 1, and the general upper bound for the norm of this W hat, which is the approximation of W prime. So the second step, after we calculate that, we want to calculate approximation of the Ritz representers of the linear functionals. And when we do that, of course, we don't have harmonic functions. We usually use some other functions to approximate. And these other functions are the phi hat. And for each one, we want to have that the error in H1 is less or equal to some epsilon 2. And again, we can choose what the epsilon 2 is. We can do the approximation to any precision in that step. However, again, we have to be optimal in choosing the epsilon 2. And then we have to, the third step is computing the matrix. So after computing the matrix, we could have some general approximations. So we do the approximations as the matrix norm from L1 to L1. And this is the one norm. And we, of course, form the, we'll have this estimate for the R, which is the difference between the G and each approximations based on approximation values of the Ritz representers. So when we do this approximation, the critical part is the analysis of the errors. So we have two quantities. One quantity is M, which is the inverse of the Gramian matrix, and the other M hat is the inverse of the approximate matrix. Because we assume that the linear functionals are linearly independent of each other, then we'll have for the original matrix that G is invertible, and then if we choose epsilon 2 small enough, we can make the approximated Gramian to be also invertible. So that's also should be taken into account. When we have this all analysis, we have two ways to measure. So sometimes we want, for theoretical purposes, to use M, because M is kind of known quantity theoretically at least. And then for practical purposes, we want to use m hat because this is what we know. So when we calculate our approximate Ritz representers, then we'll get the m hat, and so we have to have the estimates of both quantities through the other, and we have that, and then in general we receive that the differences between the inverses in L1 norm is from some quantity which we define by delta, and we can say that delta can be made arbitrarily small by making epsilon 2 smaller. And based on this analysis now, what we have, okay, I have to hurry a little bit. So we have the fourth step. So after doing that, we can find actually the solution. How we find the solution? Simply we solve the algebraic system with the approximate quantities of W and G, and find this approximate constants. We have this sum there, and then after that we can recover U by adding Q hat plus it. So I discussed what is that already in the slides, but practically we have this is our algorithm, and the interesting part of it is that the first 3 steps we can do offline, so without involving what are the data points, and then we only the 4th step, which is fairly small in terms of calculations, can be done online. And the theorem, as I said before, it is all to calculate, to have the explicit representation of the calculation of the epsilon. This delta comes from step 3, and we have this expression, so I don't think that we can talk about this expression, what exactly that means, but it means that we have the full control of the error, and we can say when we'll have this neo-optimal recovery of U. Now, I want to take a couple of minutes to talk about point evaluation data. The point evaluation data is usually, if we assume that taking a functional over h is just the point evaluation, then obviously these are not functionals which are continuous in h1. So because of that, we have to do something extra. First, we mentioned that actually we don't need them to be continuous in h1. We actually want them to solve for UH, and that's why we have to have that HS is actually continuously embedding is C. That is one of the conditions, and then in order to do that, we have to have S is big enough. In 2 dimensions, it would be 1/2. In 3 dimensions, it should be bigger than 1. And then we, however, have to calculate the values in U0, so that makes it, we have to be able to calculate there. So that is, we have this condition there, but what is important is that we can achieve that through modifying the first 2 steps. The first, in calculation of the U0, we, in addition to having that in the norms in H1 should be less than epsilon 1, we also have to have that the norms of the calculations of U0 and U0 hat less than epsilon 1. And then, in addition, in the modified step, we should have the same thing for the calculations at the data points to be less than epsilon 2. So when we add these two conditions, then we have the same theorem for the point evaluation. So that is one good thing that we can go for that. So I want to take a few minutes to talk about the approximations of the Ritz representers. So I'll be generally brief. So what we have is that by definition the functions should be harmonic on omega. The Ritz representers should be harmonic. However, in this approximation, we'll not have harmonicity, so we'll define that to be discretely harmonic. And actually, we have, so this is the definition how we do that for the Ritz representers phi. So we just define some harmonic extension operator, and based on this harmonic extension, we have this weak conditions on the Ritz representer. So that means we define that the Ritz representers through the harmonic extensions of the function phi, which is in HS gamma. And so we have some conditions. So then we can have, after this, we can have the harmonic to have the Galerkin formulation for the problem. So what we are using, we actually have the trace operator, the approximate trace operator based on the the VH. So and then we want to have this space with the zero boundary conditions, and then we can define what is the discrete harmonic extension, which is actually minimizing that operator as for the harmonic extension, but this is based on the functions in VH and getting the discrete approximation of the boundary. And then we can solve the Galerkin problem and find what are the approximate Ritz representers of the functions. So what is interesting here is that this can be used for theoretical purposes. However, when we want to have practical approximation, it is better to go to saddle point problem, in which we actually define Lagrange multipliers to find the approximation of the Ritz representers. So I want to give some talks for the and this is the discrete saddle point formulation. What is good about the discrete saddle point formulation, if we have certain quantities, so we have to have that some quantities, so pH is the number of the basis functions we have to calculate. We have to solve them in some dimension mh, and then to have, I think that, here are the definitions. So this is the dimension of one space, dimension of the second space, the third space. And when we have the calculation, so for the general Galerkin formulation, we have this approximate complexity, while in the saddle point problem we have much lesser number, which actually is used for solving the problem. So, and finally I want to finish with to say what is the purpose of that. So how we can relate to deep neural network. First of all, instead of computing grid representers with finite element methods, we can use the deep neural networks to have the similar approximation. The thing is how you prove that this solution is good enough for you. That is one of the challenges. The other one is to consider what happens. So we are solving the system, but sometimes it could prove better to receive the results directly without calculating the phi's. So can we actually shortcut that system, which eventually can be done with deep neural networks, so it could be defined, and we can define the minimization problem, which solves that, which practically would be very good for large M. So, and of course, the other problem is to consider other setups in solving PDEs with incomplete information. And thank you very much for your attention.
Thank you very much, Peter. Are there questions for Peter? Ruediger.
So I know nothing about the topic, so forgive me. But if I give you a numerical, solution or any, solution, approximate solution, if you look at the problem to determine what the error of that solution is it known whether or not that's as complex as determining the exact solution, or is there a way to find out a bound on the error that involves less than just computing that?
It is usually when, because we have residual estimates, you can calculate the error through the residual, approximately, of course, but we can have a good bound of the error through the residuals. So, and calculating the residuals doesn't mean we calculate the whole solution.
So your first question, if you train a neural net, right?
Yeah.
Then you don't. It's okay. It can just give you anything, right? That's okay.
It depends on the problem. I said in some problems with finite element methods, we can do the residual estimate. When we have general deep neural network, this should be developed. That is something which is not developed.
Okay.
In the way I like it, there's some works on the subject, but people, in order to have a really good estimate, they usually go through finite element methods, because this is what is known.
Maybe we can see the main theorem.
Yeah.
Because my comment is about the Gramian and, of course, the numerical sensitivity to the inverse Gramian or so. I guess it's natural that most people would say, if I have given measurements which are not so good linear independent, then you do some singular value decomposition or something like this. Yeah. But then the question is, you have few Hilbert spaces, and then it may be different, or it may be interesting to know, I'm not sure if this has been looked at, which one to choose. Because if you have many measurements, you may run into the trouble that this inverse Gramian, I think the capital M, is a very big number, so you do a lot of effort to do essentially some overfitting. I'm not sure if this is occurring.
Yes, this is... actually, when we consider the problem on the boundary, so the important part is where you have the data points. So the data points this linear function also, but if you consider this as data points, they could be close to the boundary, which will give us very nice and good Gramian, but if they're somewhere in the center, then it would be terrible. And we actually have some computations in the paper considering both cases and seeing what is good and what is not.
There don't seem to be any further questions. So no, yes, there is one. Okay, Sven. You're trying to delay your talk, right?
Exactly. Oh, there are many microphones. So I was wondering, what if you have noisy measurements of your lambdas? Can you deal with this?
Yes, because we practically create a noisy measurement through solving this zero boundary problem, and that's why we can treat them in the same way. This simply adds to the constants, and this formula would be slightly different, of course, in that case. But we can handle that if we have firm information of how bad that is. I guess you want to ask what if they're random and defined through that, then probably you have to change the norm from L1 to L2 and consider what is happening.
Okay, so let's thank Peter again.
Yeah, thank you.
It's a pleasure to announce our next speaker. That will be Sven Wang, who is still in Berlin, but soon to be a professor at EPFL in the mathematics department. Sven, please.
Thank you very much. Is it desired that I use the microphone, or is it okay also to speak directly to the audience? It's okay.
You should use the microphone because of the live stream.
Yes. And does anybody still have the pointer? Perfect. Okay. Great. Okay. Thank you very much for the invitation. It's really a pleasure to be here for this workshop. And so I'll speak about statistical learning of operators. At least for most of the talk. So that is this first paper that will make up the bulk of my time. And if I have time, I also want to talk about a related problem. So this is kind of in surrogate modeling for PDEs. At least these are our main examples we're thinking of. And we also have some work for parameter estimation in SDE models. Okay. So what is the general setup that I want to consider? Well, we're interested in inferring nonlinear mappings between infinite dimensional spaces. So this is something that many people in the room here are quite familiar with. I know that this is the case. So we have X and Y, two separable Hilbert spaces. We have a subset F of my first Hilbert space X, which acts as the input domain of some kind of nonlinear operator, which throughout will be denoted by G. And this G is the object of interest that I'm interested in learning from data. Okay, and I will be interested in learning that from input-output pairs, so pairs of X's and Y's. And so to a statistician like me, this looks very much like a regression problem, but a complicated one because it is defined between infinite dimensional spaces. Okay, so what we think of as model examples, of which we will see concrete instances, I will introduce a concrete example, is that X and Y are some kind of function spaces, and G, for example, encodes, let's say, a PDE solution map, right? So mapping from a coefficient living in my first function space to the corresponding solution of the PDE. Another example would be that G encodes kind of the evolution operator of some kind of dynamical system. Okay, and the idea is why would be interested in learning this G or finding a data-driven surrogate is because this might be very expensive to evaluate. So each time I have to run PDE solver. Okay, And just to give one of the main motivations, but we're not limited to that, but this is really one of the main motivations, has come from the inverse problems community. All right, so in inverse problems, people are interested in doing inference on some kind of unknown latent parameter f0 from noisy measurements of this forward object that is g of f0, right? And so people in inverse problems have been very interested in learning surrogates of g, because in the process of inferring f0, typically a lot of solves for g at different f's are required, right? So in order to invert, I need to do a lot of forward evaluations of my operator. And I'm not going to go into detail about these kind of prototypical strategies for solving inverse problems, but I want to mention them here briefly, because we can already see why this is the case, right? So people go about solving inverse problems usually following one of two predominant paradigms. One would be kind of some kind of variational formulation where you write down a loss function that typically consists of a data kind of least squares type residual term and some kind of complexity penalty, right? And so imagine if I have to run gradient descent on this objective, I need a lot of evaluations, not just of g of f, in fact, at the iterates of my algorithm, but actually also of derivatives of adjoints of g. So that, and I can already give a disclaimer, is something that we do not address, but that would be really, really interesting to address, of learning actually derivatives. Okay, and similarly, in Bayesian inversion, I equip my space of unknowns, my parameter space, as we would say in statistics, with a prior distribution, and that prior distribution is reweighted using the likelihood. And when I want to sample from this posterior distribution, I have to evaluate g of f at, let's say, different iterates of my Markov chain Monte Carlo algorithm, because g of f features here in the likelihood function prominently. Okay, so this is what I just said. And to introduce the prototypical example that we use in the first paper I mentioned, but which also serves as a prototypical example in a lot of the inverse problems and applied mathematics community for new methodology and new theory as well. This Darcy flow problem that many of you know. So I have some bounded domain, which I assume to be as nice as we want. And the map g of f is then given as the solution operator to this steady state heat equation. Right, so my right-hand side g is supposed to be some given and known source function, and the mapping g of f maps kind of this heat conductivity coefficient that spatially varies to the corresponding steady state of the heat flow that corresponds to the spatially varying heat conductivity, and we have Dirichlet boundary conditions, right? So heat is absorbed at the boundary. Here is just an example of some heat conductivity here on the left, and on the right-hand side we see the corresponding steady state of the heat flow. And so we see already that there's, at least qualitatively, some kind of smoothing going on, which obviously one can prove as well. So this is, in the language of linear inverse problems, also an ill-posed inverse problem, okay? But this operator g is nonlinear, so we want to learn this, okay? And the goal is to do it without curse of dimensionality. Obviously, that's okay? Just as a reminder, this is our goal. And here I have just, okay, before I go into our mathematical developments, some of the main methodologies that have arisen, and there are more, I know, and sorry if I'm citing incompletely. These are two of the main strategies that have become commonplace. So DeepONet stands for deep operator networks, and then here the Fourier neural operators. They have been successfully deployed, at least in some let's say, model problems. In practice, it is still case by case and can be very challenging. And so what I'm showing here is not our plot. This is a plot from the original FNO paper coming out of a group at Caltech, where they are simulating or they're considering a 2D Navier-Stokes problem on the two-dimensional torus. Okay, so here we have an initial condition that is propagated forward to time t, let's say time 1 for the sake of it. And this is what we have noisy measurements of. Right? So the forward operator G would be the operator mapping the initial condition to the terminal condition, and we want to reconstruct the initial condition, right? And so here are two reconstructions in the top middle and on the top right of the initial condition, and they are obtained, one using the classical method and one using the neural operator method. And what they showed is that empirically, at least on this example and on a few other examples, that FNOs work in terms of computational cost much quicker. Okay, and on the bottom we see the reconstruction of the terminal solution, which is something we would call maybe PDE constrained regression. Right, so there's no inverse problem, as we can see. Okay. And as a statistician, of course, I got curious, so I've taken the liberty to cite here directly from their abstract. It says neural operators directly learn the mapping from any functional parametric dependence to the solution. But obviously, the question is, how well can you do that, and can you do that with a reasonable sample size? Okay. So, what are we considering here? Later I will come back to the concrete PDE example, right? But now for maybe 10, 15 minutes, I will speak purely about statistics and an abstract setting for regression in Hilbert spaces, okay? And the setting goes as follows. So as before, we have X and Y. And now I introduce this notation that instead of G, I have G0 because we like to think about ground truths. So I want to treat the operator itself now as the unknown. So I assume that my data that I have comes from some G0, and I want to find this G0 within some class curly G. Okay? So G0 is the PDE solver, the real one. And I will specify in a moment what the distribution, what the probability law of these epsilon I variables are. Okay? So I want to do regression based on input-output pairs xi and yi, and I apologize for the change of notation, because previously I called the x's f's. So these are the coefficient functions. But in the general setting, it makes more sense with the x's. Okay, the challenge is obviously that the input variables xi are infinite dimensional, and when there are nonlinear interactions between the input variables, this is what creates the curse of dimensionality, which is well known both in approximation and in statistics. Okay, and when one is trying to do regression for nonlinear functions on which I maybe do not want to impose some very stringent structural assumption, but in statistics, that is just called non-parametric regression. And in 1D, this is or in finite dimensional domains, this is an extremely classical problem, obviously, right? So here we just see data that is some nonlinear regression function plus noise. And we see here in the blue curve, this is kind of a local averaging estimator. It's called a Nadaraya-Watson estimator, so you can think of it like a KDE. And it's very well known how to, this is amongst one of the methods with a suitably tuned bandwidth that is kind of optimal, right? And so the optimal rate you can achieve for non-parametric regression in D dimensions for functions that have S derivatives, roughly speaking. So on Hölder, Sobolev, or Bezov scales is this one. The rate is n to the minus 2s divided by 2s plus d. So when s goes to infinity, this rate will converge to n to the minus 1, right? Because we're looking at the squared risk. So this is like 1 over square root n rate. But when you have any fixed s and you're letting d go to infinity, that is a rate that will deteriorate exponentially badly in d. Namely, if you want to achieve a let's say, prescribed precision level epsilon here on the right-hand side, and you're asking yourself, how large does n have to be? Well, n will scale something like epsilon to the minus d, approximately, right? So this is the curse of dimensionality. In finite dimensions, however, I mean, this minimax optimal rate, this can be shown to be information theoretically optimal, is achieved by a number of methods. So including wavelet-based methods, smoothing is what I call, for instance, for these local averaging methods, which I showed on the previous slide. Notably, empirical risk minimization, which is arguably the most relevant for modern machine learning. Okay, and these are classical works, let's say in the 90s and 2000s. Right, Donohoe and Johnston's work on wavelet methods. Sarah van der Heer developed a lot of the theory for ERMs. Okay, but in the operator learning setting, what we found, at least when we started this work, is that one thing that was that made me very hopeful is that on the approximation side, there was for certain operators with quite strong regularity assumptions, but which can be verified in examples like Darcy flow, so namely holomorphy properties or analyticity properties, you can actually get dimension-free approximation. And this is something that the statistical literature had not leveraged at all, right? And this is a setting in which there are meaningful examples. I don't want to claim that this is that this applies, universally, but that was our starting point, right? To try to combine these kind of dimension-free approximation results with statistical learning theory, if you want, okay? To hopefully get some dimension-free statistical rates. And we did not know whether we would be able to obtain anything meaningful. Okay, so now I'm finally ready to be a bit more rigorous. So what do we assume? We suppose our xi, so our input coefficient functions, are sampled IID from some kind of probability measure gamma that for now can be any probability measure, any Borel measure on x, okay? And we assume this is kind of our data generating process that we observe the pairs xi, yi with noises that are themselves, because now G0 of xi are elements in some function space y, right? So what is a canonical assumption for additive noise in a Hilbert space? I would argue that the most canonical noise distribution is a white noise process, right? And I will motivate that, I will qualify that in a second, why this can be viewed statistically as a natural assumption, right? But that's something we had to ponder about for quite a bit. Okay, so we'll assume that these are IID Gaussian white noise processes, meaning that the covariance structure of this epsilon I is given by the inner product in Y, right? And if you want to think about it pictorially, if Y is the L2 of some domain, right, then this white noise process will essentially just be spatially independent noise. For any 2 points, you have uncorrelated noise, okay? And why is this statistically kind of a reasonable continuum model? Well, the reason for that is that, okay, and here I'm making an analogy. This is not proven for this setting in operator learning, right? But at least for finite dimensional non-parametric regression, white noise observations can be shown to be statistically equivalent to kind of equally spaced discretized measurements, right? And this is a deep result actually from Le Cam theory, where you say in the limit where you have more and more equally spaced discrete measurements with IID noise, so independent noise, crucially, you'll kind of, in a statistical sense of closeness of statistical experiments, come to the continuum limit of this white noise model, right? So estimators have essentially achieve the same quality. In particular, minimax rates are the same, etc., etc. This is for multi-dimensional non-parametric regression. It's a result by Markus Reis in 2008. In this setting, it's yet to be proven, which is an interesting, I don't know about important, but interesting open problem, in my opinion. Okay. So this is my noise assumption. Feel free to interrupt me at any point if you would like to ask questions or challenge this. Okay. And the estimators we're looking at are empirical risk minimizers. Okay, so we would like actually in principle to write down this kind of least squares objective. And this is essentially what we do, but one has to be careful in infinite dimensions. So essentially, so when my space Y is infinite dimensional, and these Yi's, remember, contain the epsilon i's, which are the white noises, then epsilon I almost surely will not actually constitute a well-defined element in Y, right? So if I take an isotropic Gaussian in infinite dimensions, that will not take values in little L2. That's essentially it. And so I have to modify this objective. So what I can do, I can formally subtract the Yi norm squared term, because that plays no role, at least formally, in my minimization problem, right? And so the empirical risk minimization problem I actually consider is that formed by the remaining two terms by expanding the square. And that is a well-defined measurable function in G. Okay, and so I can try to pick an argmin. So these are the minimizers G hat n that I will consider. And in fact, interestingly, this is also, in infinite dimensions, it's difficult to write down a likelihood function with respect to Lebesgue measure. There's no Lebesgue measure, right? But you can still find a common dominating measure for all of these possible data generating distributions come from different G's, and the dominating measure will just be G equal to 0 centered white noise, right? And then this is exactly, in fact, the likelihood function. So the Cameron-Martin theorem for Gaussian processes tells you that this is the likelihood function, and in fact, these G hats are the maximum likelihood estimators. So this is very well qualified, okay? Okay, so now I want to introduce some assumptions on the operator class curly G, under which we can prove something. Okay, and this is very much motivated by the theory that Sarah van der Geer has developed in finite dimensional regression, where she said you have some class of regression functions, and under general entropy conditions on that regression class and approximation properties, these are the two ingredients you need, you can say something about the quality of the ERM over that class. And this is what we do for the operator learning setting, okay? So I have two assumptions. The first one is some kind of uniform boundedness assumption, which is the less important one, right? So I need that my class curly G is bounded in this L infinity of gamma norm, where L infinity of gamma, remember gamma was the measure my xi inputs are sampled from, is the essential supremum of the Y norm of G of x over that, over the support of gamma, okay? The more crucial assumption is the following, is an assumption on the metric entropy of this class curly G, and the metric entropy needs to be taken again in the L infinity of gamma norm, right? So this is what it turns out. I've already gotten the question by several statisticians whether this assumption can be weakened to a weaker notion of entropy, and we haven't been able to do so. Okay, so what is this metric entropy? It's the logarithm of the covering number for my class G to cover the class G with balls of a given size delta with respect to this L infinity of gamma norm. And we're making an assumption on the growth of this entropy. Okay, so we want this entropy to blow up at most at a polynomial rate, delta to the minus alpha, as I shrink my radius delta, and this exponent can be at most 2. And in particular, what this implies is that when I integrate the square root of h of delta, that converges. And this is very much, those of you familiar with Gaussian processes and empirical processes, this is what enables to use, Dudley metric entropy bounds, etc. So this is very classical assumption in the finite dimensional case. And so here we have a theorem for the kind of infinite dimensional case. So the loss function we're looking at is kind of this mean squared error, right? So it is the expected squared error for data coming from some G0. And the loss function I take here inside is the L2 of gamma norm. right? So in a way, this is like L2 for real valued functions, but now instead of the Euclidean norm on R, I'm taking the Hilbert space norm of Y. So if Y is actually just R, then I get the usual L2 mean squared error. But here I get it with respect to the Hilbert space norm. So it's a bit of a Bochner square integrability condition, not really, but it's it's a bound in this norm. And what we get is kind of the following theorem, that you can upper bound these errors by the sum of an approximation term, which is kind of the best possible L2 gamma approximation in your class, plus a stochastic error, which is of the order n to the minus 2 over 2 alpha. Okay, so the smaller alpha, the slower the blow up of the entropy, and the more this rate converges again to the n to the minus 1. Okay, and you can ask the question, well, the one obvious question is, for example, that if I consider the finite dimensional regression case, or the case of regression from RD to R, what do I get here? Well, then alpha, by classical results, for the entropy numbers of Bezoff spaces, with suitable smoothness indices, the entropy is known to scale like delta to the minus d over s. Okay, so this is like the inverse of the effective smoothness, and so this will recover then the optimal, the minimax optimal finite dimensional rates that we saw earlier. Okay, but this is a generalization to the infinite dimensional case, and I know there's a time estimate there. Oh, I'm doing not bad. So, okay. The proof works through, as I mentioned, so this is really inspired by these M estimation techniques developed by Zara, but also actually Birger and Massal, who studied minimum contrast estimators at the end of the 90s. But one really had to dig up the empirical process machinery that built on. And the empirical process machinery that was used in here is general enough also to handle these Hilbert space valued functions. And that is, seminal work by Lagrange. So this is the latest edition of his book. But we specifically use bounds from this very nice paper by Sjoerd Dirksen. And I want to tell you a little bit how generally one goes about proving these bounds for ERMs, both in finite and infinite dimensions. So first of all, instead of studying the L2 of gamma norm, which is ultimately our target, it is very convenient to consider the so-called empirical norm. And that is the norm arising from my evaluation points xi, all the inputs that I've evaluated my G0 at. And why is that? Because the functional is formed using these xi points, right? And so what one starts with is this kind of basic inequality. So by definition of the minimizer, I know that for any other G star in my class curly G, my G hat n has a smaller objective than this G star, right? And by simple completion of squares, you can actually derive this kind of inequality there that tells you the following, that at least in the empirical risk, not in the target risk of L2 of gamma, the G hat n exceeds the empirical risk of G star only by some right-hand side that is a stochastic process. Okay, and the stochastic process on the right-hand side is driven here by the epsilon I, the noise variables, and the noise variables are kind of interacting with G hat. And the whole complication is actually that G hat and epsilon I are not independent, right? Because G hat is formed using data, and in particular is in fact somehow a measurable function actually of the epsilon I. And so this is not easy to control. And this is why you need this kind of empirical process theory, right? So you take a supremum on the right-hand side to deal with this correlation. But intuitively, what this basic inequality is telling you, and this is really like 2 lines going from here to here, or from the definition of the ERM to here, this basic inequality is telling you that if G hat is to have a large risk, it can only happen if you are on a small probability event, hopefully, of a large fluctuation of the epsilon I. Okay. So what is this stochastic process that one has to control? Well, here it is a stochastic process that is now not indexed by time or something, but it is actually indexed by the operator class that you have, right? So I mentioned that here, in order to get rid of the hat, which is the thing that induces dependency, I'm just going to take a supremum over my whole class curly G, which is an incredibly crude method to employ. But then when I've taken the supremum over G, I get a, I need to control suprema over, essentially this process xg for G and curly G. Okay, and now I have no dependence any longer. Okay, and now this is, these kind of peeling arguments is something that Sarah ingeniously invented. So you can control, so this is the target probability I want to control. What is the probability of my empirical risk being bigger than some level R squared? And then you do a so-called peeling, meaning that you decompose the probability into deviation probabilities of suprema of this xg process over increasingly large balls. Okay, and I'm happy to tell you offline what these increasingly large balls are. But essentially, what you then end up having to control is the probability that these xg processes are larger than a certain threshold, right? Okay, and then it becomes a task of kind of controlling the metric entropy or the complexity of this process. And the good news is that this process xg is a sub-Gaussian process with respect to a certain metric. And this metric is exactly the L infinity of gamma metric. And so this is why you need to control the complexity of this operator class in exactly this metric. Okay? So that informs our condition. And then you can use kind of well-known tools from empirical process theory to bound these suprema. And essentially what you get is that the threshold, the expectation of these suprema are essentially 1 over square root n times the integral of the square root metric entropy in this L infinity gamma norm, right? And excuse me for the kind of, I'm not giving you enough time to read everything, but I'm happy to talk about it more offline. But that is essentially the proof sketch for this general result, okay? Okay, so now I want to mention how this can be actually verified, at least in some meaningful examples. So my goal was to develop a non-empty general statistical theory, and that was challenging, and that was why it was amazing to collaborate with experts in numerical analysis. Okay, so in practice, what do people do? Well, they discretize both in the input space and in the output space to some kind of basis representation, and then they truncate those basis representations and a high-dimensional neural network or some other approximating class is used to represent or approximate these operators between infinite dimensional classes. Okay, so this is something people here in the room have worked on extensively. Okay, so what the setting we are assuming is that actually the basis representations are fixed. They're not learned, and learning them is also definitely something that is done in practice. Okay, so we're fixing bases, or to be precise, frames, okay, for x and y, and once you have chosen such a frame, such as, let's say wavelet expansions or Fourier expansions on your function spaces, you obtain kind of smoothness classes that are intrinsic to this basis representation, right? So in the case of wavelets, these functions would be somehow like, roughly speaking, Hölder-Zygmunt classes, like Hölder classes, right? So these are spaces intrinsic to your representation that you have chosen, that within that representation satisfy a certain decay condition on the coefficients, right? Okay. So we need these smoothness scales in a moment. So that's why I'm introducing them. So XR and YT, so there are two smoothness indices, R and T, and you can think of them essentially as Hölder classes if you want. Okay? So I made a very nice commutative diagram. So essentially you can go between each of these separable Hilbert spaces to L2, and then you can view your operators G as mappings between sequence space. Okay, and so these are going to be called encoders. So encoders encode into a sequence, and decoders that decode from a sequence to back to the function space. Okay, and so then this is how the neural networks are kind of mapping between these truncated coefficient spaces. Okay, and as I mentioned before, there was kind of a well-developed theory for approximation of PDE operators that have certain nice smoothness properties, and this was really started in a paper by Cohen, Devore, and Schwab in 2010 or 2011, I think, where they didn't show holomorphy to begin with, but analyticity of these operators. But holomorphy is a sufficient condition. And the holomorphy says essentially the following, that you assume G0 is defined on some kind of open neighborhood within the complexification of my input space X. And the open neighborhood is an open neighborhood of this kind of smoothness ball of a sufficiently large index. Okay, and you assume one complex derivative exists in the Fréchet sense. Okay, so that this operator on this open neighborhood OC can be linearized using some, at each point X in OC, using some complex linear and bounded operator between XC and YC. Okay, so this is in some sense like the holomorphy definition in first complex analysis class. And the second assumption is that somehow you need this G0 mapping to be bounded over this open neighborhood. And it needs to be bounded not just in the Y norm, but in the YT norm. Okay, so there needs to be some kind of smoothing or compactification going on, and there are conditions on these indices. So this R needs to be bigger than 1, and T needs to be bigger than 1/2. Okay. Okay, so this I'm simplifying here a little bit. So in reality, this condition is a little bit weaker, but that's the essence of it, that you need some kind of boundedness in some higher norm, and you need holomorphy. And under these conditions, it was shown not just for neural networks, but originally for polynomial expansions, that you can get dimension-free approximation, right? So I'm just going to go quickly over this slide, because as always with introducing neural network classes, there are many parameters flying around, so it's heavy on notation, but maybe most of you are familiar with it. Anyway, so here we are looking at neural network classes of mappings between input dimension P0 and PL+1 with depth L, width P, so P is the maximum of all of these intermediate widths. And crucially, size S, right? So there's some kind of sparsity parameter that governs everything. Okay? And essentially, ultimately, we're coupling all these choices of these hyperparameters by saying they all depend, they're all chosen with reference to size S neural network class, right? And essentially what the approximation theorem says is that if you have this kind of two assumptions that I stated on the previous slide, you can approximate your G0, which satisfies these regularity assumptions, by a G star, which is a neural network of size S. Okay, and you get the approximation uniformly over this smoothness ball, XR, right? So this uniformly over Hilda ball, let's say, right? Okay, with a certain rate, which is essentially S size minus twice the minimum between r minus 1 and t, and here nu is an arbitrarily small perturbation. Okay. And so this is obviously compatible. This is one of our ingredients for the general theory. The second ingredient is to obtain entropy bounds for these neural network classes that are growing at least polynomially, which is actually possible. And so what you can then get as an application is, for example, a dimension-free statistical convergence rate in the Darcy flow problem. Okay, so the Darcy flow. So here I'm looking at a slightly modified version. So I'm looking at it on a torus. So that makes dealing with boundaries easier. And I'm therefore looking for solutions that have mean zero, okay, to ensure uniqueness, okay. And so here we're making a certain choice of X as a Sobolev space with sufficient regularity, and Y is L2 of O, right? And so if you remember in our noise model that we considered, the epsilon I, the noise variables were white noise processes with respect to this L2 inner product. And so that in particular means that we are indeed taking the continuum limit of these discretized IID N01 noises. Okay, and then what you can get is essentially a polynomial quote-unquote dimension-independent convergence rate. I mean, the discretization dimension is not even featuring here because the loss is on the level of the operators. So what do we have here? We need that this gamma is also supported on a sufficiently nice inputs of x. So okay, you can ask the question, what is XR here, right? So XR will certainly contain Sobolev and Hilda spaces of sufficient regularity, but it is not clear what exactly they are characterized as. But let's say sufficiently smooth functions, okay? And you can get an algebraic rate here on the right-hand side. I mean, with some convergence n to the minus rho, and rho here can be quantified. I didn't write it out. We're not sure whether it's optimal. We're currently trying to work on lower bounds as well. Okay, but this was really exciting, at least to me, because that was kind of the goal. Okay, so that's all I want to say about operator learning. Now, just to maybe very quickly mention that there's another line of research we're pursuing. So if anybody is interested in talking about this, I would be happy to chat, but I will be very brief on this. So this is inference for diffusion processes. So this is like very related to inverse problems, but with a time sequential nature, right? So here, in these kind of problems, I don't have data from the solution of a PDE, but I have a solution to an SDE that I'm seeing, right? And here, so I have some drift vector field and some diffusion coefficient B and sigma, and I'm interested in estimating B and sigma from discretized measurements, okay? And so when these measurements are kind of far in time, so there's a finite time distance that does not assume to be close to zero, then this is a difficult problem because the likelihood function is given by the transition densities at a fixed time gap of this Tx process. So that if you want to evaluate that, you have to solve the Fokker-Planck equation, right? So one thing we did was that, okay, so here you can see the kind of setting that the data is what you see here on the right-hand side is this kind of discrete time transitions, and this is the continuum time, but unobserved diffusion trajectory, and you're interested in recovering the thing on the left, right? Okay, so you want to infer the thing on the left from the thing on the right, okay? And so this is another setting in which your likelihood is kind of given through PDE, in this case the Fokker-Planck equation. And what's particularly difficult is to calculate gradients. And in many algorithms you need gradients For instance, if you want to compute maximum likelihood estimators, you want to do gradient descent or ascent, right? So we essentially developed gradient formulas for differentiating with respect to the parameter, the Fokker-Planck equation. Okay, and it turns out that this is a completely purely PDE argument, but you can derive from that some kind of formula for the infinitesimal perturbation of your transition probabilities, and using that you get nice and quite fast algorithms for, let's say, computing maximum likelihood estimators or sampling using Langevin methods. So any gradient-based numerical scheme. I'm mentioning this because I know there are also several people in the audience who are working on solving high-dimensional PDEs, which I'm like have a huge respect for. And our methods, we use finite elements, right? Okay, but this gradient formula should, in principle, also hold in higher dimensions. But actually, evaluating this formula requires PDE solvers. So if there's anybody interested in chatting about this, I would be quite keen. And I know that I'm at the end of my time, so I will just go to this final slide with some references, and also would like to mention, I mean, as Helmut mentioned, in the fall I will be moving to Lausanne, and there will be some openings for PhD/postdoc positions. And so if any of you has knows somebody of whom this could be of interest, I would be keen. Yeah. Thank you.
Thank you very much, Sven. Philip has the first question.
I have a question about the results on operator learning, or more about the example. So the example that you showed uses basically as a main structural assumption the holomorphy. And basically it's known that for that the optimal thing to do would be like a polynomial chaos expansion or something like that. And so I'm wondering why one would use neural networks for this. I'm very doubtful that it would come close to a polynomial chaos-based algorithm in terms of efficiency.
Yeah, there's a very, very reasonable question. And to be completely frank, to me, the main appeal of our work has nothing to do with neural networks. It is really to kind of exploit those regularity properties that have been known to be satisfied by PDE problems with statistical theory. And you can show exactly the same results for polynomial chaos expansions. And in fact, it simplifies a lot the minimization problem, obviously, of the empirical risk, because it becomes a convex problem. And I know that Jakob, my collaborator, he has implemented some of these methods with his students, and in the examples that he has looked at, as far as I can tell, you know, the polynomial expansion methods are extremely good. Yeah. So, yeah.
Peter?
Considering the general setup, you usually talk about Sobolev smoothness, and that means global smoothness. Can you go to local smoothness, say best of spaces? Best.
So you mean X and Y being...
No, in general, when you talk about, you always say, okay, we could have Sobolev or Hölder smoothness.
Yes.
And which is global one.
Yes.
And you could have, say, in a lot of wavelet-based problems, you have local smoothness. So that means you go to best of spaces. Can you get this transition in the results?
I think that a lot of our theory carries over in very much the same way as non-parametric regression, you know, doesn't rely on your function space being a Hilbert space. One technical difficulty here is why we look at the Hilbert space setting is even in order to formulate the noise model rigorously that we consider here, you need to consider Y to be a Hilbert space, the output space. But you can always, I guess, use embeddings between those spaces and Bezoff spaces to get some consistency result, meaning some rate, whether it will be optimal or not, I don't know. And we also consider actually other noise settings. So where you have a sub-Gaussian noise, not necessarily of this white noise structure. And there you can generalize, but we haven't written this out. So I don't want to. It's not a theorem or proven, but I'm quite optimistic that it would be possible. Yeah.
Thank you.
Hans, please.
Yeah, when I see the word frame, I always think that frames are in Hilbert spaces, and it connects with the last comment. Frames are in Hilbert spaces, but Hilbert spaces are also, that's my statement, social beings. They always come in families. So you should think of Banach frames, and I mean, wavelets are a good example. They are the family of function spaces, the classical function spaces were around, and Calderon-Sigmund operators were started, and suddenly we could understood because you have analysis, synthesis, and not in a bad way where you say, choose the space and then I give you a constant, but there is a constant that is good for a whole family, maybe a compact family of parameters where you choose the family appropriately for your problem, which gives you decompositions. And I think that's one of the key points, I think, also in your story, that you should choose the right Banach frames for appropriate families of atomic decompositions, which are linear, maybe you have to do it adaptively or so, and then you have probably a very, very good chance to get other problems. So kind of widen the scope of, I mean, I see very classical function spaces here from the point of view of function spaces.
Thanks. Thank you. So perhaps I can close with a question. If you can go to slide 13, please.
This is a limited speed, the pointer.
Yeah. Yeah, if you can, yes. So, I mean, if you have the unit interval, and so the metric entropy is log 1 over epsilon. If you have Lipschitz mappings, mapping RD to R, the metric entropy is epsilon to the minus D. And if you have truly infinite dimensional to infinite dimensional sequence to sequence mappings, let's say with a Lipschitz, fading memory assumption, then there are two ways how the memory can decrease, exponentially fast or polynomially fast. In the first case, it's E to the 1 over epsilon, the metric entropy. In the second case, it's E to the 1 over epsilon. So that I would consider truly infinite dimensional. So I'm trying to understand how I should, because this to me looks like it's actually Lipschitz functions, right? Because it's delta to the minus alpha.
It's Lipschitz of finite regularity functions, right? So in 1D, in 1D, alpha would be 1 over smoothness.
Yes, exactly.
And so in D dimensions, it would be
D to the
D over
divided
smoothness.
by S, right?
Yes, exactly.
So
in fact, you're absolutely right that, I mean, and there are lower bounds, I think shown by people here and others, that show that when you have just a Lipschitz assumption on infinite dimensions, you can't really say anything. I think the interesting scaling limit, in a sense, that we're taking here is we are, in fact, looking at smooth operators. So they're C infinity, and they're defined on an infinite dimensional domain, and there's some kind of compactifications through these decaying sequences.
Right.
And so then, in some sense, we're looking at in a non-asymptotic way, kind of at the approximation quality by representation systems. And somehow you can, in that scaling limit, end up with things that are not worse than the complexity of these classical spaces that you have mentioned, yes. So in some sense, our assumptions are quite a lot stronger than what you have mentioned, yes.
Yeah. So if you replaced the upper bound by a 0 times E to the 1 over delta, probably you would have lots of problems in the derivations, right?
Yes, absolutely, yes. So then, I mean, already the metric entropy integral doesn't converge.
Yes.
and then you have to do some different method. You can still use some kind of empirical process theory, but you will end up almost certainly with logarithmic convergence rates. So that of, let's say, severely ill-posed or severely high-dimensional problems. Yes.
Yes. Okay.
Yeah.
Okay. Great. Thank you very much.
Thank you.
Good. Thank you very much. So we have a coffee break and we reconvene at 11 o'clock.
Approximationsresultat so ist. Genau, weil die sparsity Annahmen und so. Also bei der Ursache ist ja noch Beholung auf die, oder? Da ist ja in manche Richtungen jetzt eigentlich. Ja, genau. Okay.
All right, welcome back. Just a correction. The group photo after the second talk, now after Philip's, the talk after Philip's will be here. And then Bill McCall is here. He is actually one of the founders of the Lagrange Center. He will say a few words, and then we can go for lunch. And an updated program will be printed soon. And today in the afternoon we finish at 4:15. There's a coffee break, and then you're free to roam around, and we'll meet for dinner at 7 o'clock. So it's a great pleasure to introduce our next speaker. I just looked at the title and the name, and I was almost about to say the next talk will be given by Erwin Schrödinger, but no, it's actually on the Schrödinger equation, and it will be given by Philipp Gross from the University of Vienna. Please.
Thank you. Sorry. So, but nevertheless, I hope that what I'm saying will be interesting to you. So basically, I suggested several talk topics, and this one I also suggested to Helmut, but I wrote him that basically there is not a lot of mathematics in it. So this started out as a kind of a side project in my group, in computational science, I would say, on solving the electronic Schrödinger equation. And it was so successful that it kind of branched out and became one of the main areas of research that we're doing. And the purpose of today's talk for me, so my goal is, first of all, to explain the problem and show what we could achieve. And also I would like to convince maybe some of you that this is actually a cool topic, and there are very interesting and nice mathematical questions that arise. So maybe some will become motivated, and so that would be great. Okay. So the electronic Schrödinger equation, it's kind of a PDE problem. Solving it with deep learning. No, first of all, okay, that's probably very important. So here are the main contributors to this work. So Leon Gérard, who was a PhD student of mine, he's now at AstraZeneca. Michael Scherbeler, who is really, I would say, the driving force, so a brilliant former PhD student, and now postdoc in my group. And Raphael Reisenhofer, who was also a postdoc in my group. So the Schrödinger equation is a PDE, and solving it with neural networks, that's something that people have been doing at least since 2019. So these PINs, physics-informed neural network, maybe most of you are aware, just that you have like a PDE and some boundary condition, and you generate samples on your domain and on the boundary, and then you kind of formulate like an empirical residual loss, and this loss you minimize over a class of neural networks using the usual stochastic gradient descent or similar, like first or second order algorithms, and in the end you hope that you have found a good approximation to your solution. And the rationale for doing this is often that you can prove that in an approximation theoretic way, the neural networks are kind of optimal. So one can often prove that neural networks, if you knew the PDE solution, so there would exist a neural network with a very small one that approximates this solution to any desired accuracy. So there are very strong
approximation results, and also it's very simple. So if you have if you have written your code and you would like to consider a different PDE, well, basically you just modify one line in your code, you modify the loss, so this F maybe, and you can write another paper on another PDE. So there are literally tens of thousands of papers on that, and I have to say that generally I'm not a big fan of this method. Mostly, so if you look at papers, it's often they show, like when they evaluate their methods, they show a picture of their numerical solution. It looks a little bit similar to the true solution, and often that's how far the evaluation goes. But in truth, you should evaluate like how much time do you have to invest to get a certain accuracy, right? There are a few papers that do that, but those that do, well, I mean, then it doesn't look so great. I mean, if you want to solve like a two-dimensional Poisson equation, which would be like a matter of maybe a fraction of a second or so with finite elements or spectral methods, it takes like hours to get 4 digits of accuracy, and similar for other problems. So usually these methods actually don't work that well. I think that's fair to say, especially if you want to have high accuracy, if you want to have like 5 or 6 digits of accuracy. This doesn't seem to be possible for most problems, and there is also a fundamental reason for this, which I'm not going to really go into. But one problem of neural networks is that they are very sensitive to the information loss that you have when you only have point samples available. So you need lots and lots of point samples to kind of nail down a neural network, even if it only has very few parameters. And this is not true for other systems like finite elements, where you basically need a number of samples that is comparable to the dimension of your finite element space, and then you have basically the function identified. And for neural networks, it turns out that kind of in terms of samples, the convergence rate is reduced, so cannot really be better than a Monte Carlo rate of 1/2, and that's not really acceptable for many PDE methods, which are usually tuned to have high approximation rates. And so for me, like a rule of thumb is if you have a PDE and you have classical methods, probably it's a good idea to stick with those, but there are also other PDEs where you don't have classical methods, and one of them is the Schrödinger equation. So kind of a provocative summary is like for standard pin results, you do have approximation results, but in practice, often it kind of doesn't work that well. We don't really have any mathematical results, and I would like to change that. But it does work extremely well. So electronic Schrödinger equation. So now I want to describe the problem that we will talk about. I have to start with a brief intro to quantum mechanics. Classical mechanics. So you have a point in phase space. So P is momentum and X is the location. So that's just one particle in 3D, let's say. And you have an observable, so this is just some function of x and p. So in classical mechanics, basically the location and the momentum, they determine the state of the system. And quantity of interest, the fundamental quantity is energy, which is often like a sum of a kinetic energy term and a potential energy. So this H is often called the Hamiltonian. And we all have learned like it's like Newton's law, which can be translated, so it's a second order ODE, which can be translated into the so-called Hamiltonian ODE. So basically the propagation is done by this Hamilton equation, and so this is how the system propagates in time. And you might be interested how some measurement evolves with time or whatever. So basically, if you know the initial condition, you know the equations that govern its time evolution, and basically you know everything. Quantum mechanics, instead of having a system described as a point in phase space, you have a function in a, let's say if it's particle in R3, a L2 function, a normalized L2 function, and basically states are identified if they are a multiple of each other, a scalar multiple of each other. And observables, so these are modeled by self-adjoint linear operators, which are typically unbounded operators, so they're not defined everywhere. And if you remember from your functional analysis course, self-adjoint operators have a nice, very nice structure. So there is the spectral theorem, which basically represents any self-adjoint operator as an integral over a so-called projection valued measure. So if A were a matrix, these projections would just be projections onto an eigenspace. And so you could directly write that. So it's an easy exercise for matrices to write them as such a representation. And the important thing is that if you have this spectral representation, you can have an probabilistic interpretation for measuring the observable A in a given set omega. And this probability is just this projection valued measure. So this projection valued measure is defined on all measurable subsets, so of omega. So basically you project onto the spectral subspace of A that is associated with omega, and you look how much remains, how much it is correlated with psi or so. And this gives you kind of a probabilistic interpretation of measurement. And okay, we have this measure, and one has a general procedure to quantize classical observables, which I'm obviously not going into, but basically the momentum is a gradient multiplied by I, by the square root of -1, and the position operator is multiplication with x, and then you can quantize basically this energy observable, and you get this operator here, the Hamiltonian, and then you get the Schrödinger equation, and this is basically just a unitary one parameter group with infinitesimal generator -I times h, and it preserves the norm of the energy. So that's quantum mechanics, and it's a, I mean, I probably don't have to say that it's a very fundamental theory. First of all, it kind of illuminates somehow stochastic nature in certain measurements, like the double slit experiment, and it's also very crucial in proving that matter is stable. So here we have a small molecule, and there are electrons orbiting these nuclei, which consist of positively charged particles, and they attract each other, and classically, basically, these electrons would collapse into the nuclei and would release an infinite amount of energy, and only through quantum theory one can prove that fortunately this doesn't happen. So that's kind of very fundamental theory. So in my talk, I want to study the Schrödinger equation, or the quantum mechanical properties of molecules. And molecules are defined, as I said, by nuclei. These are capital R1 to capital Rm. And they have three-dimensional coordinates. I consider them fixed, so they do not move. This is called the Born-Oppenheimer approximation. And there are electrons, which are kind of orbiting these nuclei, and basically I'm interested in the electronic wave function. So this is now not a function of only 3 coordinates of one particle, but of these n coordinates. So it's a function of all the electron coordinates, R1, R2, R3, R4, R5, 6, 7, 8, 9, 10. Yeah. So this would be a 30-dimensional function. And basically this wave function, one can interpret it as a probability density. So if it's normalized, the probability that you get a certain configuration, so this fat R, it's just all the electron coordinates. This is just, well, the integral of omega with respect to this density. Okay. And yeah. Yes? Yes? Well, here the space of, in the discrete, you mean the space of functions on these particles is 2 to the dimension. And here it's the same thing, so you also get a cursive dimension. So, yeah, as we just heard, these are interacting particles. So, here is the energy. So, this models the kinetic energy. This term is a Coulomb repulsion between 2 electrons, so they repel each other. This term is a repulsion between 2 different nuclei. So this is a term that actually doesn't depend on these coordinates, so only on the nuclear coordinates. And this is a Coulomb attraction between the electrons and the nuclei, because the nuclei are positively charged and the electrons are negatively charged. And these Z's are the charges of the nuclei, and I'm using here dimensionless units, so there are no Planck constants or things like that in here. Okay, so that's basically this defines more or less the system. And if you have some wave function, you can measure the expected value of the energy. So this would be just the inner product of this Hamilton operator applied to the wave function, inner product with the wave function divided by the norm squared if it's unnormalized. So that's the expected value of the energy. And we are particularly interested in the case where where the wave function is an eigenvalue of an eigenvector of this Hamilton operator. Now, why is that? Well, first of all, if this is an eigenvalue, one can show that the spectral measure. So I told you before, you get like a probability distribution where your observable is. So if you have an eigenvector, this probability distribution is a Dirac. So you have like a Dirac, so a deterministic energy. Only for eigenvectors you can actually deterministically assign to it an energy. And what is more, one can show through rather deep results that the spectrum of this Hamilton operator, it kind of splits into 2 parts. So you have a minimal energy, which is called the ground state energy. So the spectrum of this operator is lower bounded by this ground state energy, and it turns out that this is actually an isolated eigenvalue of finite multiplicity. And this means, for example, that there is not an infinite amount of energy that your molecule can absorb, so it cannot explode. Well, it can, but I mean, there's a limit somehow. And then there is usually not all infinitely many such eigen values, and they cluster at a certain point, and this is called the ionization threshold. And above this ionization threshold, one has continuous spectrum. And usually states that are in this continuous spectrum, they are delocalized. So, for example, this might consist of conformations that are not bound to each other. So two systems that move separately away from each other also. And the systems that are that are linear combinations of these eigenvectors, they are so-called bound states. This means that their shape doesn't really change with time, so they kind of remain stable. And in generally a system, a molecule tries to assume its lowest energy. So this is usually how under normal conditions the wave function looks. So we want to find the ground state and the ground state energy of such a molecule, and maybe also the first or second excited states, but I'm not going into this. But this is a fundamental quantity that we are interested in, and this gives us basically a description of what the molecule looks like. There is another thing. Electrons are indistinguishable. So this means if you permute the coordinates of the electrons, it should not change the state. And basically, I told you that states are equal if they are a scalar multiple to each other, and the scalar should have absolute value 1. So that's written here. Now, one can show, and that's actually not too hard, if you impose this condition, you get basically two types of symmetries. You can either get particles where this C is equal to 1 always. So basically the wave function is symmetric under permuting the electron coordinates. These are called bosons. And the other possibility that you have is that the C is equal to -1 to the power of the signature of this permutation. So basically this means if you just swap two different electron coordinates, you get a -1. So this function then is antisymmetric. And this is then called, so particles of that type are called fermions, and electrons are fermions. So actually we get an additional structural complication, namely we are not really having as our Hilbert space, we don't have like L2 over 3n coordinates, but we have to restrict these functions to be antisymmetric. Okay? And that's, I mean, it's easy to be easily written down, but if you develop a numerical procedure, I mean, you have to respect this. I would also like to say that I find it very nice that actually this this constraint that the wave function is that the electrons are fermions and the bosons has dramatic consequences. So one can show, for example, that somehow stability of our matter crucially lies on this fermionic nature. So it's kind of if you have this restriction, the ground state energy will be larger than if you would not have it. If you would have if you would have bosons, and if our matter would consist of bosons, for example, if you would have two rocks and you put them together, they would release a lot of energy and probably so it would not be so nice. So there's very beautiful work by Lieb and so on who on that. We are interested in numerical methods. So this capital R, it encodes the positions of the nuclei. And this is the ground state energy. So this is the smallest possible energy that the system can assume. And so this is just the Rayleigh-Ritz principle. I'm looking for the smallest eigenvalue, and I'm just, minimizing this Rayleigh quotient, right? I mean, I guess it's, and I have to minimize it over antisymmetric H1 functions, H1 because that's just the form domain of this bilinear form. Okay. And now if we assume we had this, we would get what is called the potential energy surface. So for each conformation, so this means this capital R is just the location of the nuclei, you get the ground state energy. And this gives you basically all information that you would want about your molecule. So for example, it gives you information on how your molecule will actually look, because the nuclei, they will assume positions that minimize this potential energy. And it also gives you information, so the gradient of this approximately contains the forces between nuclei, and so you can run molecular simulations. So that's kind of really maybe the most fundamental quantity in computational chemistry. And okay, I mean, there is of course decade-long research on that. So here is just one. I mean, there are many applications, but if this is the potential energy surface and parametrized over some distances of nuclei, and if you want to simulate like a chemical reaction, so you have these two separated reactants, and you somehow want to track the transition path. So how much energy do you have to spend to get over this hill where they can eventually react? So that's kind of a crucial question. And doing this would be searching like saddle points and like over this potential energy surface. Another thing would be, as I already said, molecular dynamics. So if you have this potential energy surface, you can compute forces between different atoms, and you can run, like time stepping schemes, ODE solvers to track the dynamics of your molecule. So these are quite fundamental quantities. And so there are lots of applications. So also, I showed you like this discrete spectrum, these spectral lines, and basically they determine the wavelengths of radiation that such a molecule can emit. So in that way, you could, for example, try to identify which compounds are present somewhere in outer space or so. Of course, it's also fundamental in material science, where you would like to measure properties, which are basically functions of, which usually can be computed from the potential energy surface, or like drug discovery or so. And there is a famous quote by Dirac, which many of you might know, that kind of so we have the law, the Schrödinger equation. You can write it down in one line, so it's very easy. But solving it is kind of not really possible. So it's just very hard. And the first thing I want to say is why this is a hard problem. Well, the obvious thing is we have high dimensionality. I mean, if you have even a couple of electrons, like 50 electrons, you have a 150 dimensional PDE eigenvalue problem. That's not easy to solve by any means. You have like The other thing is, it's not enough to solve it to a couple of digits of accuracy. It's not enough to solve it for 3 digits of accuracy. We want to be as good as an experiment. So there is a certain inherent experimental uncertainty, which is called chemical accuracy. And this is the expected accuracy for such a simulation to be considered useful. Another reason why we want to be accurate is, so the total energy is usually around some hundreds of Hartrees. So that's just a unit. But we want to study reactions. So we want to study relative energies. How much energy do I have to spend if I want to modify my system a little bit? And these energy differences, they are on a much smaller scale. But we have to resolve them. So in general, our relative accuracy has to be on this order, 0.02%. Let's say we have 100 electrons, 300, which is still not very big. I mean, for a chemist, we have a 300-dimensional PDE eigenvalue problem. We want to solve it to an accuracy of 0.02%. Not easy. So we have a Coulomb potential. The functions will have singularities. Yeah, it's an additional bonus. Yeah. I mean, we know where these singularities are and how they look. So it's actually kind of possible to kind of remove that. Yeah. So how do you usually deal with such a problem, classically? The first thing is we have to find an efficient way to generate antisymmetric functions. So fortunately, I mean, that's also actually, I find surprising that you can kind of evaluate an antisymmetrization operator in polynomial time. It's remarkable, I think, so via the determinant. So here is an ansatz. It's kind of an antisymmetrized tensor product. So you have n different one particle, so-called orbitals, and then you put them into a so-called so you assemble this matrix, and you compute the determinant. And that's basically the same that you would get if you just consider the tensor product of these functions and antisymmetrize it. Yeah, it's the same thing. And this is antisymmetric, of course, right? I mean, if you swap two particles, you change here a column, and then, okay, it's multiplied by -1. Okay. But already you have a complexity n to the 3 just to evaluate this thing. I mean, it costs something. And if you have like many, many hundred dimensions, this is not so nice. So now, okay. There is something called a Jastrow factor, which I'm not going into, but that's kind of a prefactor that you can multiply in front, and this is usually used to kind of to remove these cusp singularities. So one can prove that if you do this, kind of the regularity of the remaining part is enhanced. Then what you do is basically you take like a low rank approximation and antisymmetrize these low rank functions. So you take many of those Slater determinants, linear combinations of them, multiply them by a global function. This global function has to be symmetric in order to not destroy the antisymmetry, and then you get an approximation. And then you can ask, well, how many of these Slater determinants do I have to take in order to get a certain desired approximation error? And there are even very nice results. So the strongest results I know is by Hari Iseritant from 2010. And he basically exploited some, so hyperbolic cross approximation or so. Very nice result. And basically you get the dimension independent approximation rate, -1. So for the experts, usually if you do like hyperbolic cross approximation, you get in front an unpleasant factor like log of the error of 1 over the error to the d -1 or something like that, which would again destroy the approximation results. But due to the antisymmetry, he was actually able to remove this, which is very nice. But there still is a constant in front, and it at least grows exponentially. So again, the constants are not effective, and therefore the result is not really practically useful. And if you want to go to chemical accuracy across various different systems, you can do that until maybe 15 particles, but then one would have to use some other tricks or so on, and yes. That's just, you know, the number of Slater determinants. Yeah. Okay. And there is a whole zoo in computational chemistry. So the simplest is Hartree-Fock. You basically take one determinant, and depending on how many determinants you take, you get like increasing complexity, and usually coupled cluster, triples, whatever it is. I'm not going to go into it. It's considered the gold standard method, and it can handle like maybe 50 electrons or so. But also depending on the system. There is one outlier here. It's called density functional theory. Again, I'm not going to talk about that either. So that's kind of a completely different approach. It reduces the problem to finding a one electron density, which is only a three-dimensional function, but it relies on some models, on auxiliary models that are usually not very precise, and you usually don't get a very good, very accurate solution, and there is no systematic way to improve it, but it was awarded the Nobel Prize, and it's still, I mean, it's usually the most used method because it can handle systems with thousands of electrons. Yeah, and often the accuracy is sufficient for several applications. So, okay. So neural networks, Ansätze. So here is an observation. So somehow this low rank approximation, if you just consider a rank 1 approximation, it treats the system as if it would consist of completely independent particles. There are no correlations between them, except for the Pauli exclusion principle, but other than that, there are none. So one way to build in also dependence on the other coordinates is to consider so-called generalized Slater determinants, which depend on all variables, but only on the first it depends in an arbitrary way, and it's symmetric in all the other variables. And then you can, this just means all coordinates except for the first one, all coordinates except for the nth one, and if you put this in, and again you permute two columns, you get -1. So this is still an antisymmetric function, but you can bake into it correlations. And one can show that actually with O of n, such generalized Slater determinants, you can represent any antisymmetric function. And maybe this can even be reduced to O of 1. I think so. So that's kind of a very general way to represent antisymmetric functions. And now, what one usually does is to compute these functions, you compute one permutation invariant embedding that embeds your electron coordinates into a high dimensional space, let's say 256, and that's permutation invariant, and these phi i's, they are just basically you compute a feature vector for each I. Also in this 256 dimensional space, you compute this inner product, and you also add like an envelope function because ground states, they have some exponential decay and you would like to enforce that. And okay, that's your answers. So, and these functions, they satisfy these symmetry conditions by construction, and you can put them in here in this determinant, and you can try to approximate the ground state by such a sum of a few, actually in our case it's 4 such parametrized determinants. Let's say 4 is what we will have. And the typical way that this permutation invariant embedding is constructed is by a graph neural network. So you start out with initial features, like let's say the distances between an electron to all the nuclei, or the difference, and then 2 particle features, which are basically distances and differences between 2 different electrons, and then you have some kind of message passing. So you start out with those original features, and then you pass messages around, and the end feature is basically the invariant embedding. So that's kind of something that one can conveniently compute. And then you can try to minimize this Rayleigh quotient over these parameters, which make up this message passing. And this is done, okay, I will get into it if I have time later on, by a iterative pipeline. Okay, maybe I get into it later, but it's a bit similar to what one usually does in deep learning, but there are things that are also different, but one can do it. And okay. And this was pioneered like in 2019 by Hahn and Ö. The results were not very good at that time. Then in 2020, there were 2 breakthroughs where, like, for systems like hydrogen chains with 10 hydrogen atoms, one could get accurate results, which was at that time already quite good. So it's 10 electrons. And yeah, and ever since, this has improved. So this is like one work of our work from 2022, where we got at that time, most accurate published absolute energies for molecules with up to like 40 or 50 electrons. Absolute energies, you can say, since this is a variational method, so this Rayleigh quotient is always an upper bound for the true energy. So you can kind of say if you're lower, you're better. And that's kind of what we did here. Okay. And just as a side remark, I mean, I just said relative accuracy is 0.002% or so. Well, it turns out that actually the energy error is bounded by the function space error squared. So at least for measuring the energy, we can kind of at least double somehow the rate. Yeah, and that's maybe this is a reason why this works, but I don't really know, to be honest. So we also consider transfer learning. So we want to study usually many systems at once, and so we constructed an architecture that doesn't depend on the size of the molecule, and that's actually quite challenging because usually the number of coefficients in your neural network, they somehow depend on the size of the system. But we succeeded in that, and we trained kind of a foundation model on some random conformations of different sizes, and then we tried to evaluate it or fine-tune it on new unseen molecules, and that works very well. So so you get good speed-ups, and basically you can, so from this foundation model, if you do like a couple of fine-tuning steps, which are computed quite efficiently, you can basically get the accuracy of current high accuracy methods, which is quite good, but much faster. Okay. And we also did this for solids, so you can compute interesting properties of solids, but I'm not going into that. I want to say a little bit about the most recent contributions, which is finite range embeddings, where in this message passing, we only consider electrons, so we only pass messages between electrons that are at a certain small distance apart. And this basically speeds up all our calculations by an order of magnitude. And in particular, you could say, well, this really reduces the expressivity, but so here, so this is just an evaluation of the speed, so it's just reduction by an order of magnitude. I mean, that's previous complexities, and that's kind of the time for our new architecture. But what is even nicer is that it is at least as accurate as previous approaches. So yeah, so there are many strongly correlated systems here, and we compared them. So here we're getting in the range of 200 electrons. So this is a protonation energy of iron-sulfur complex. So you have this iron-sulfur complex, and you have 4 sites where you could add a proton, and you want to know where it will land. So you have to compute where you get the lowest energy, and this is very subtle. You have to be extremely precise, and So it's possible to compute this. So if you do this coupled cluster, you get much bigger errors, which in particular do not resolve this. And and this is another challenging system, ionization potential of chloroferrocene, which also has, I believe, way over 100 electrons. But 180 electrons to chemical accuracy, that's quite big. So that's almost a 600-dimensional PDE. And this is a kind of a stupid slide, but this is the creator of this Fermi-Net paper and writes you can start to tackle real challenging chemistry. And this is previously impossible systems. So I think that's pretty cool. I mean, 5 years and now this just works better than other things. I mean, it's compared against experimental values, and it just can do things that had previously not been possible. And I think we still have an idea to significantly improve this. Unfortunately, this is the first time I'm holding this talk, so I had a hard time to estimate the time. There are many nice mathematical questions, but like convergence rates, sampling theory, approximation theory, and a posteriori error estimation, but you will have to talk to me offline to get to the technical questions due to lack of time. So here is my conclusion. So I think this is really cool. I mean, 5 years, not even, and I mean, that's like a really important problem. It's not like some exotic problem. So that's, and I think it's almost ripe for real applications. And I would like to stress the mathematical questions that I did not mention, but that I'm happy to discuss. Okay. So here are some publications, and yeah, again, as some others, also looking for excellent students. Thank you.
Thank you very much, Philip. Questions? Sven?
Thank you. So I'm curious if you, let's say, run your neural network solver, a posteriori, are you always able to verify whether it has given you a good answer? So let's say we don't have, nice mathematical theory, but, there's some kind of wave function given to you. Do you have a way to check whether this is close to the actual ground state that you wanted to find? It's a bit like P versus NP.
Not really. I mean, but this goes also for the other methods. So there is no methods at that scale. All methods have dubious guarantees. I mean, there are the results that exist. Usually, they are in terms of the energy variance. And if you know, like the spectral gap, so the gap between the ground state and the first excited, so the first two eigenvalues, then you get an estimate, also a lower estimate on the energy. Through the variational principle, you have an upper estimate, so in principle you have it. But usually these intervals, if you will, confidence intervals, they are very wide. It's not so easy to narrow them down to like chemical accuracy. That's a generally difficult problem. Again, this is something I have some idea also from spectral estimation, because basically the spectral measure that you have is a sparse measure. It's a linear combination of Diracs, because you're in the discrete spectrum, and there exist many methods. So I would be interested in exploring ideas related to that. But as of now, there do not exist for any method like reliable, like really, really useful a posteriori estimates.
Thank you. Further questions? Maybe I can ask one. What you went very quickly, you said graph neural networks and so on, and then you showed your results. So what was it in terms of algorithmic tweaks and tricks that you applied that kind of led to this big speed up?
So the big speed up, I think that now there was a really a jump basically by an order of magnitude in our most recent work, and this was because this graph neural network, usually in this message passing, you basically collect messages from all electrons in your system. And now we only collect we only collect information from only those electrons which are very close to the original electron, like within like 2 bond lengths or so. And this reduces the complexity by a magnitude, by an order of magnitude. And this itself is not, and there are lots of clever things where you can use this. For example, if you update this determinant, then if you just modify a single electron, you get like only a low rank update, and then the determinant of a matrix plus a low rank perturbation can be efficiently computed and so on. And so this, in summary, reduces all operations basically by an order of magnitude. The surprising thing that I don't understand is that you don't lose accuracy through it. And even, I mean, I could not really go into it, but I can, I mean, just takes a few seconds. If you increase the cutoff, you don't really get a big improvement in accuracy. So if you say you have a large molecule which has like 20 or 30 angstrom size, still if the cutoff is only 5 angstrom, you basically get the same accuracy. So you don't really lose anything. And this is something that I find surprising, but I don't have an explanation for it.
Great, thank you. Do you know, so AlphaFold also uses graph neural networks, right?
Yeah, but AlphaFold basically operates on a different level.
Yeah, sure.
So we are operating really on the bottom level.
Yeah.
So we are basically on the subatomic level, basically, where we really have an ab initio method where we only start with the Schrödinger equation. AlphaFold uses already force fields, for example, like pre-computed, like you would have to do this before. But I think a good application actually of all this stuff would be to generate high quality data for simulations that that are basically on the mesoscopic scale.
Yeah. So that means we should all be studying graph neural networks, because I kept joking about them until a few years ago. But
well, I would probably also find it. I mean, I think so, because it's a different approximation procedure, and we should understand, or I would like to understand, how an approximation theory for such functions in terms of these graph aggregation methods, and I'm not aware of it. It's obviously existing theories with classical smoothness paradigms, and they are not really useful.
Okay, thank you very much. All right, if there are no further questions, let's thank Philip again. And we can proceed to the final talk this morning, which will be given by Samuel Landthaler from the University of Vienna. Generative AI for statistical computation of fluids. And I think then we will probably have had enough of PDEs, and we can all go to lunch after that, please.
Okay. So yeah, thank you for the introduction and then invitation to speak here. So to conclude this kind of session on maybe more scientific computing applications of deep learning, I'll be talking about applications of deep learning in fluid dynamics. And this will be more akin to the talk of Sven, where we are trying to not only approximate individual solutions of these equations, but actually to approximate the whole solution operator, or a discretized version of that. Okay. So maybe let me give you a short outline. This talk will be very kind of not filled with math, but I'll just try to get across the main ideas of this work. And there's a lot of math in the appendices, as you often have with these machine learning papers, where you can find the details. So basically, I will start with just introducing the problem setting that we have been trying to address. In short, what we want to do is learn the solution operator of some turbulent flow. So you map the initial condition to the solution at a later time. And then I will kind of go through some empirical observations that we see. And what I will try to highlight is that we see some very contrasting kind of results that we get depending on how we formulate the learning problem. Okay, and in particular, I will refer to one approach as the deterministic approach and the other approach as the probabilistic approach. Okay, and then, well, once you have very differing results depending on your formulation, then the question is, why does this happen? And that's where the theory comes in. That's what my contribution basically consisted in, to try to understand why we see differences between two formulations. Now, if you don't care about scientific computing, then maybe you can still get something out of this talk, because the broader question is that, well, the problem formulation actually often matters in machine learning. And here we try to find an approach where we can kind of address this question in this specific instance. Okay, so let me start with the problem setting. The setting is exactly as what Sven had explained before. So I assume we have this solution operator between two function spaces x and y, and we assume that we are given data in the form of input and output pairs under this operator. And the goal is to find an approximation of this operator within some parametric class of operators, which in practice, of course, is a neural network. And of course, in practice, the input and output spaces will not be truly infinite dimensional, but they will be discretized versions of these infinite dimensional spaces. But this in practice leads to, say, a million dimensional input space and a million dimensional output space in my examples. Okay. And as I said before, I'm interested in approximating these solution operators in the case of fluid dynamics. And what we wanted to do here is to go to this very challenging case of turbulent flows. And my operator here, again, it will take as input a flow state, which will be my initial data, and it will give as an output the solution at a later time. Okay, and you can think of this t here as being just a fixed time, lead time that you want to predict over. Good. Okay, so now I should write down some equations. So I'm just writing down the incompressible Navier-Stokes equations, which we will look at in this talk. And we are considering a setting where the Reynolds number is very large, or where this right-hand side term, which is a diffusive term and regularizes the equations, is kind of small, right? And when you look at this setting, then this comes with two main challenges. The first challenge is that these flows tend to be very unstable. So this means that if you give an initial state and you perturb it just slightly, then, well, the initial state will be perturbed very slightly, but if you evolve this in time, like the trajectories will diverge very quickly. Okay. So that's the first main challenge. It's not only a challenge for learning, but it's also a challenge for just general numerical schemes, right? And the second challenge is that these types of flows, they actually have a wide range of active spatial and temporal scales. So this means when you discretize these equations numerically, then you will have to deal with a lot of degrees of freedom. So these are truly high-dimensional kind of problems. Okay. Yeah. So, for example, if you expand your flow field in terms of its Fourier series, then the coefficients will decay quite slowly. Good. Okay. So now, to explain some of our empirical observations, I will mainly focus on this shear flow example. What is a shear flow? Basically, what we take as initial conditions here is a three-dimensional flow field, and you can think this as being in a periodic box. Okay, so with this flow in a periodic box, and everything here that is in red is basically the flow going this way, and everything that's in white is the flow at rest. And these two flow states are separated by quite a sharp interface. And basically what happens is that this is kind of a well-known case where you have strong instabilities. Along this interface that separates the two flow states, you will have that the flow will develop very strong turbulence, right? So you have a kind of turbulent mixing layer that forms. And then dynamically, you go from something that's quite ordered in the beginning to something that it is has all these turbulent small scale features. Okay, and there's this kind of messy flow state at the final time. And again, what we want to do is to learn the mapping that goes from these types of initial conditions to this type of final state. And yeah, so our initial conditions basically will be, we take a flat interface and we will make kind of random perturbations of this interface to generate our initial conditions. Good. So let me now go to what we actually observe when you try to formulate this as a learning problem and just run gradient descent. And again, I will highlight two approaches to formulating the corresponding learning problem. One is the deterministic formulation, which I'll go into first. Okay, so what do I mean by the deterministic formulation? Well, it's essentially just what you would naively do, right? So what you want to do is you want to take this as an input and make a neural network predict this as an output. So you can go ahead, generate your data with a numerical solver, and then basically minimize some empirical loss where you have your neural network, you put in your known initial conditions, and you try to regress on this solution at a later time. Okay. So mathematically, often, I guess one formulates it as sampling initial conditions from some measure. The measure here would be just random perturbations of this interface. And mathematically, it's kind of minimizing some mean squared error. Good. And, well, I guess I wouldn't be giving this talk if this naive approach worked at all. And actually, it doesn't work at all. I mean, it's really, really bad. So this is a case where what I'm showing here is like ground truth on the top. So these are 3 different solutions obtained with the numerical solver for 3 different initial conditions, so the random perturbations of this interface. And after training, I mean, our best model kind of predicts this. Okay, so this is terrible and completely useless. And, well, okay, so at best, I guess the way you could interpret this is that you take the top picture and you kind of wash out all the small-scale features. So somehow the model maybe has learned about the coarse-grained features, but it doesn't learn at all about these turbulent features. Okay. And we've tried, well, I haven't tried, but my collaborators on this project have tried a lot of different architectures, and we see the same exact behavior for, like, whether you use some kind of vision transformer or some convolutional architecture or some neural operator architecture. It's basically all leading to the same conclusion that this approach just doesn't work. Maybe I should also say that these models were trained on like 10,000 data samples. So we basically took 10,000 initial conditions, made the random perturbations, ran our numerical solver in 3D to produce these 10,000 flow states at later times. And that's the way we trained our neural networks. So I think in terms of the scale of generating this data, that's already quite large scale. I mean, so probably in practice, if you wanted to make this practicable, you couldn't have much more data. Okay, so scaling up data is probably kind of reaching its limits here. Okay, well now, the first approach is that you kind of just don't look into these types of problems anymore, and you go back to your more nice problems where you can easily like fit your neural network and claim very great things about Fourier neural operators or whatever. But here we wanted to really push this. And so we wanted to find a way to make this work, okay? Because in applications, many flows are turbulent. So if this is ever going to be practicable, we want to be able to treat also these turbulent flows. Okay, and basically one idea that we had, kind of if I frame it in a naive way, is to say that, well, you know, these guys in machine learning, computer vision, they are very smart. They have found ways to kind of generate very high quality images, for example. And basically, what I want to point out is that they have found ways to train neural networks to produce outputs that actually have a lot of small-scale features. For example, this fox here, like the hairs on this fox, I mean, they are super high resolution, right? And that's very different from what we see with our naive training, where all the small-scale details were washed out, okay? So then the question is whether if we apply this type of method to our kind of scientific problem, whether we can also recover more small-scale details. In our case, small-scale details are exactly the turbulent features. Great. Okay. So what do these models do, and how do they frame their problem to get these high-quality results? So basically what they are doing is they are trying to sample from some kind of conditional distribution. Okay. So here, what they want to do is they sample from conditional distribution where U here would be this image, so an array of pixel values. And they want to sample not just any image, but they want to sample specific images, so they impose some kind of conditioning variable. Okay, and the conditioning in this case would be a text prompt, for example, a fox looking for a socks. Right, you run your model, it will produce some sample from this learned distribution, which is this fox in this case. Okay, great. So maybe I should at least try to explain how this is actually done in practice. So this is my attempt at having a one-slide kind of explanation of denoising diffusion models. At a high level, so the goal again is to sample from this kind of conditional distribution. And denoising diffusion models, it's actually a very nice mathematical formulation. I suggest everyone to read into this topic. It's It's super nice. But the idea generally is that you define two processes. One is the forward process, one is the backward process. The forward process is very simple. Basically, all you do is you take your known image and you just add noise to it. So white noise at various levels of magnitude. Okay, so this is basically you go from this picture and you add noise to it. And at some point you have added so much noise to it that you can't distinguish the fox anymore or the picture anymore. Okay, and then the idea is that, okay, this is a very simple to define forward process. It takes you from your distribution of images and produces a distribution of pure noise, essentially. Okay, wouldn't it be nice if we could invert this process? So basically, if you could invert this process, what you could do is you just sample noise, which you know how to do, and then you somehow want to be able to move back towards this image distribution. Okay. And it turns out that there's a very rigorous way to mathematically formulate this, which involves like some mapping that one has to learn, which is the denoiser. Okay. I won't go into the detail of this here, but essentially the conclusion of this is that what you have to do to be able to invert this process is you train a neural network D. This is my denoiser model. And you kind of have to train it on a simple mean squared error loss. Right? So this is similar to what we had before. And what is this neural network trying to do? So essentially what it's given is a noisy version of your image, okay, at some noise level sigma. It's given the conditioning that we want, so that the neural network knows that from this noise I want to push towards images of foxes, for example. And it's also informed about the noise level, okay? And then you basically take randomly an image, you take randomly a noise level, you take randomly an instance of this noise and the conditioning. And what you try to make the neural network do is to take the noisy image and produce the clean image from it. Okay. So this is a very nice kind of formulation, which leads to a very simple loss to optimize. It's very similar to the naive approach from before. Okay. Okay. So now how do we apply this to our case? Well, we want to sort of frame our problem, which is kind of deterministic. You take the initial condition and solve forward in time to get the output. We want to frame this as a probabilistic problem. And so the way we phrase it is that we want to sample from this conditional distribution where we are given the initial condition. And basically we want to make the model sample from the output, the solution at a later time, given this initial condition. Okay. Now, a priori, this doesn't make any sense because secretly we know that given this initial condition, I run my solver forward, I get one deterministic map. So actually this conditional distribution here is just some Dirac delta. Okay. However, crucially, we don't tell the neural network this. Okay. So the neural network will learn some kind of conditional distribution. And this is kind of the relaxation that is important in our problem. Okay. Good. So I hope I've kind of explained what these two approaches are. So again, the deterministic approach would be just regression on the solution operator. This directly approximates the solution operator by a neural network. And then we have the second approach, which is the probabilistic formulation, which trains this denoising diffusion model. And the aim of this model here is to kind of approximate the conditional probability or of the denoising process that is associated with this denoising diffusion model. Okay. And yeah, so again, it kind of, in theory, approximates some kind of Dirac. Okay. Now, what is very nice about these two approaches is that you can run, or you can train neural networks using the exact same data set for both of these approaches. Right? For the left-hand side, you just regress on this given data. For the right-hand side, well, you just sample this initial data and the solution at a later time from this same data. Okay, so we can kind of have an apples-to-apples comparison between these two formulations of an identical problem. Okay, and well, in short, these models do amazingly well in the sense that they recover all small-scale or recover many small-scale details. Okay. So again, I'm showing the same ground truth solutions obtained with the numerical solver on the top. So these are three different independent solutions for different initial conditions, which are not shown here. Then we train our denoising diffusion model. It produces these outputs by conditionally sampling from the distribution that it has learned. And again, this is very different from what we see with the deterministic model. Okay, so basically whatever is claimed for the vision tasks and the small scale details, you can definitely see them here. Okay. Now, at first, this is very nice, and if you do computer vision, then this is the end of the story. But if you want to apply these methods to computational science, then I guess you have to ask, is it actually accurate, right? Is it not only looking good, but is it actually good in some quantitative way? And unfortunately, like these samples, they are basically not very good, okay? If you, for example, look at, well, what's a good example? Maybe here, this area here, you know, and you compare it to the ground truth, then you can see that the model has generated all these small scale features, which kind of qualitatively look good, but quantitatively it's completely wrong, okay? So basically it produces all these small scale features, but all of them are essentially wrong, okay? And so the question then is, well, is this somehow better? So is this actually better than this down here, okay? And well, at first sight, like if you just care about L2 errors between outputs, then no. But maybe that's not what we should care about in this fluid dynamics case. Okay, so maybe we care more about like, do they capture some physics of the true solution fields? Now, one very kind of simple thing we can check whether this contains any physics, so whether the neural network has somehow understood physics contained in these true flows, is to look at energy spectra. Okay. So maybe for those who are not doing fluid dynamics, what is an energy spectra? So essentially what you do is you take your flow field, you decompose it into its Fourier coefficients, and basically you look at the energy that's contained at some given wavelength kappa. So this E kappa here is the energy at wavelength kappa, where you kind of integrate or you sum over the shell the square of the Fourier coefficients. So this tells us how much energy is at some wavelength. Okay. And the bottom here shows like when we actually evaluate these energy spectra, for example. By the way, very different energy spectra from before. So this is for individual flow states. Then, yeah, maybe this is the shear flow from before, so let's focus on this one. Basically what I'm plotting here is the energy spectra from the ground truth in blue, the energy spectra that's predicted by a generative model in orange, which is matching very well, and for comparison, the energy spectra that are predicted by the deterministic approach. Okay, so now as you can see, like our generative model actually captures this very well. So somehow it actually, yeah, like it assigns the right amount of energy to different wavelengths in our flow. The deterministic model is well, it's over smoothing, so you can see this here in the faster decay of the energy spectrum. Okay. Okay, so this is kind of a first hint that maybe the model has learned something useful about flows. Okay, but then, well, if you want to make it more quantitative, ask what has it actually learned, maybe it's a good moment to kind of sort of step back and ask what can we even kind of hope to ever be able to predict about these flows. So if you have a turbulent flow, then even if you run a numerical solver, you usually wouldn't expect to actually predict point values of the flow field at a later state, like true values, right? So at best, usually what people try to do is do some kind of uncertainty quantification. So yeah, basically uncertainty quantification. So how would you do that with a deterministic model? Well, with a deterministic model, this could be your numerical solver, or it could be the learned model from a deterministic approach. What you would do is, for example, you would be given some initial data. Okay. Now, instead of just predicting the output for this individual input data, you would perform small random perturbations of it, reflecting maybe in practice your uncertainty about what exactly this initial state is. And you would solve, so now you get an ensemble of initial states, and you would kind of evolve this ensemble, right? And then from that, you can compute things like the variance or the mean flow and other useful like quantities related to uncertainty quantification prediction. Okay. And then, okay, so this is what you would do classically with numerical methods, what people also want to do with these surrogate models. And what we will compare this to is in our probabilistic model. Well, again, we are given the same initial data, but now basically the idea is, well, our model actually already has learned some kind of conditional distribution. Okay, that's just how we phrase the problem. Now, what we will compare this approach to is we will just, well, sample from this learned conditional distribution, okay? And we will take this as our uncertainty quantification prediction from the probabilistic model. Now, a priori, there's no reason why this should have anything to do with the left-hand side, but it's some kind of uncertainty quantification prediction, okay? So we can compare it at least. Okay. And now it turns out that this is actually somehow the implicitly learned uncertainty from the model seems to match the kind of deterministically evaluated uncertainty quite well. So this is illustrated here. So basically what we did is we start from one instance of this shear flow. We make very small perturbations around it. We evolve this ensemble forward in time. This gives us our ground truth uncertainty quantification or uncertainty prediction. And on the left here, you can see kind of the mean flow resulting from this ensemble. And what we will do is we will fix one point in this flow in an area that's kind of interesting. That's where all the turbulence happens. And we will ask, like, okay, we have this ensemble now. So if you evaluate at that point, we have just a bunch of flow vectors or velocities. Okay, this has some kind of distribution, and we compare this distribution on the right-hand side. So on the x-axis, you have the velocity values, and then like how many members of this ensemble have been in some bin, right? It's on the left-hand side. So this is like the density in velocities at this one point. Okay, and again, we are comparing the true distribution in orange. It's kind of done here. Then we have the deterministic model, which we evaluate. I mean, maybe the ground truth, I should say, is obtained with a numerical solver following this approach. The green curve is obtained with doing the exact same thing, but replacing the numerical solver by the surrogate model. And the blue curve is just whatever has been implicitly learned by our diffusion model. Okay, and as you can see, like these actually match quite well. And well, like the deterministic model, it's a bad surrogate on individual instances, but it's also a bad surrogate for doing uncertainty quantification. So it's kind of, it goes hand in hand. Okay, and we didn't only try this for the shear flow, but also for some like more isotropic turbulence, and basically we see the same thing, maybe even in starker contrast, where we have the ground truth again, then we have whatever has been implicitly learned by our diffusion model, and if you do this ensemble prediction with the deterministic model in this case, it actually just collapses to like the mean value essentially. Okay, so definitely this diffusion model seems to have learned something useful. Okay, it somehow has learned to do uncertainty quantification for us, even though we haven't trained it to do that. That's kind of amazing. Okay, and we did many other, well, I should always say my collaborators did all of this. I'm just here kind of showing you nice pictures that I have not really put much work in, but basically we see this for various instances where, for example, for nozzle flow, you have the ground truth, you have the probabilistic prediction, you have whatever a deterministic model produces, so it's lacking small-scale details. Same for some cloud shock interaction, same for some convective boundary layer, which has to do with atmospheric physics. Okay, so this seems to be very generally true, that deterministic models fail for this type of task, whereas diffusion models seem to capture statistics really well. Okay, and uncertainty quantification. Okay, so maybe just to summarize these empirical observations, I was kind of putting this contrast between deterministically trained models and these conditional diffusion models. And for the deterministic case, we saw across a wide range of examples that they always seem to lack small-scale details. They do not match these energy spectra. And in general, like maybe qualitatively what one would say is that the outputs generally looked averaged out in some sense. Okay, you have these washed out outputs. In contrast, these conditional diffusion models, they seem to accurately reflect small-scale structure, at least at a qualitative level. They match the energy spectra well. And, well, I would say that the outputs kind of look like true samples. Okay. And so given this background, the question then is why? Why is this happening? Okay. Can we somehow understand why the problem formulation in this case made such a big difference, and why we learn this uncertainty quantification implicitly with diffusion models? Okay. And this is basically where you have to develop some theory to try to understand what's actually going on. Okay. I'm asking why, so maybe I should ask why not. Okay. And the reason why you would not naively expect this stark difference between the two approaches is that if you actually look at what these models are trying to optimize, so you just look at the loss functions or functionals, and you look at minimizers of the deterministic approach and the probabilistic approach, then it turns out, and this is actually very easy to show, that the minimizers of both functionals are identical. Okay? So the optimal, if you kind of do unconstrained optimization of this functional, the optimal denoiser is actually exactly just giving you the value of the solution operator. Similarly, okay, if you look at this loss, obviously like the minimizer is the solution operator itself. Okay. So if you want to try to understand why there's a difference in practice, well, firstly, it must be that actually neither the diffusion model nor the deterministic train model actually succeed in minimizing these functionals. And it just turns out, I mean, that they fail in different ways. Okay, so that's kind of the message. Okay. And then the question is, well, can we understand more about this than just knowing that both fail and they do so in different ways? Okay. And basically our ansatz here was to say that, okay, like the unconstrained minimizers of these functionals, they are identical. However, in practice, the minimizers that we obtain are not identical. That must mean that there's some kind of constraints that is not taken into account by looking at just the functionals themselves. Okay. So in practice, there are some constraints. Where do these constraints arise from? Well, one obvious one is that we have finite model capacity, which means that maybe our models are not rich enough to even represent the underlying solution operator here. Or, well, the model is just optimized by gradient descent. Who knows where this will converge to? Or maybe we don't have enough data, right, training data. So that's another constraint. That's kind of obvious. Now, it's very unclear, and I mean, I guess many people are working on this. It's very unclear what these constraints then lead to in practice, right? So what these imply, basically. And so basically our approach here was to not try to exactly understand which constraints lead to which sort of imperfections in the minimization procedure, but to just replace these constraints by a hypothesis. And our hypothesis was basically that models in general, they seem to be biased in some way towards stability. Okay. So we all know that neural networks, you over-parameterize them massively, but they don't overfit. Okay. This tells us that there must be some kind of implicit regularization going on some bias towards stability, as I will say it here. So what this basically means, so what does stability ultimately mean? It means that you kind of have a limited input sensitivity. And maybe to make this a bit more mathematical, although not very precise, I want to assume that there is some small epsilon, which depends on all these constraints, and this kind of depends on your training, such that if you take two inputs, which look very similar to each other, which are close to each other, then basically the outputs also look close to each other. Okay. So you could frame this in terms of Lipschitz constants or something like this. Okay. But basically, I want to say here that the model somehow is not really able to distinguish these two inputs if they are too close together. Okay. And now based on this hypothesis, I want to then analyze the two formulations and figure out what the implications of this will be. Okay. Okay, and here's the intention. So the hypothesis is that we have this characteristic sensitivity where our model cannot distinguish between inputs, but the underlying solution operator is super, super sensitive, okay? So it will not have this property, right? You can give the underlying solution operator things that are basically very, very close together, but these trajectories will diverge very quickly because the situation is so unstable, okay? And so we basically have a mismatch between the class within which we are trying to approximate this S and the properties of the underlying S, right? And it turns out that the consequences of this mismatch depend heavily on the problem formulation. So what we will do is we will apply the same hypothesis of stability to this neural network here and to this neural network here, and we will see what the conclusions will be. Okay. Now, I will not go through the math, but I will try to just illustrate the main idea. So, okay, we now have this kind of mathematical setting that we can study. And we can study it, for example, for the deterministic approximation problem, where we have some kind of constrained approximation, where, for example, we're trying to approximate some function to regress on this cosine, okay, which has a relatively high frequency. And the assumption is that although the underlying map here has a high frequency or is very sensitive to small perturbations of the inputs, that our approximant cannot match this sensitivity. Okay, so the ground truth basically varies on a scale of like 1 over k, but the approximant, I will assume, varies on a larger scale of L. Okay, and basically the conclusion is that your model basically cannot do much, right? Because there's a mismatch. So what is it supposed to do? It cannot match the values at the top at the same time as the values at the bottom. So basically what the model will do is it will kind of give you something like a mean of the input. Okay. So this is kind of a collapse to the mean, where you basically take the mean over the length scale, like that's kind of the sensitivity length scale of your model. Okay. And how is this different for the probabilistic approach? So we'll make the same assumption, but now the main difference in the probabilistic approach is that you have these kind of highly oscillatory mappings, underlying mappings, which are highly sensitive. And we're kind of interested in the limit as you have more and more sensitivity. Okay. Now, I said at the beginning that basically the formulation here is that instead of viewing this as a deterministic mapping, the graph of a deterministic mapping, the way the model is viewing this is just as a probability measure on this two-dimensional space, which happens to be concentrated on a graph. Okay. So to the model, it cannot distinguish whether this is a true graph or it's just a two-dimensional probability distribution. And it's trying to learn this two-dimensional probability distribution. Now, what happens when you take the limit as your underlying mapping becomes more and more sensitive is that this graph actually fills in more and more of the space, right? And in fact, if you took the limit, the relevant limit of like infinite oscillations, then it would fill in a whole two-dimensional distribution in the space. And so the limit in the probabilistic sense of this kind of sequence of mappings that become more and more sensitive is actually an object that is probabilistic, which is no longer supported on a graph. Okay. And this is exactly like if you run the math and you look at what the neural network is trying to optimize, it's exactly learning under the smoothness constraint, it's learning, or regularity constraint, it's learning exactly, basically replacing this graph by some filled in distribution. And this is effectively why it's learning to some kind of uncertainty quantification. So going back not to this one-dimensional toy example, but maybe the higher dimensional example, what one can show in some hand-wavy way at least, is that if you assume this kind of characteristic sensitivity for your models, like your diffusion model or the deterministic model, then under this constraint, what you will learn in the deterministic setting is basically that the model will learn for a given input u bar. What it will learn is some kind of expectation in small perturbations of the underlying solution operator, where you kind of input your u bar, but you add just random perturbations to it. And the size of these random perturbations is exactly the kind of input sensitivity, right? So you cannot distinguish these very fast oscillations in the one-dimensional example, but you will replace them by just an average over these fast oscillations. Okay. And of course, from this, you can kind of also see that if your underlying solution operator is very stable, then basically adding a small perturbation doesn't matter, right? You can just do a sort of first-order expansion of this, and you will get as main term the true solution operator applied to u bar, plus noise, which kind of cancels out. Okay. Now, the beautiful thing is that in the probabilistic setting, this expectation over delta u is replaced by the law, okay? So instead of learning just the mean of all these outputs, by running the exact same argument, what you will learn is to this conditional probability distribution, which is the law of the true solution operator applied to u bar, plus these random perturbations, okay? And this just pops out of the assumptions and the mathematical analysis, which I'm not going through today. And which kind of explains why the model implicitly has learned to do uncertainty quantification. Okay, so that's very, very nice and useful for these types of applications. Okay, yeah. So basically this talk, what I've tried to highlight is that the problem formulation in this instance of fluid dynamics depends a lot on how you formulate the problem. And I think a very good way of trying to understand this maybe more theoretically is just to impose some kind of useful assumptions. And then once you have the assumptions in place, you can then do analysis, mathematical analysis, and just see what the conclusions of these assumptions are. And I hope I've managed to illustrate one case in which this maybe leads to some understanding of what's going on. Okay. And also my plug is that a central ingredient in developing some theory here was to actually have an underlying well-defined mapping. Okay. And I think applications in scientific computing are really great for this, especially for this operator learning, because the underlying mapping here, after you discretize, it is naturally going to be a very high dimensional mapping. So you don't have to invent your own mappings with some regularity properties or whatever, but you just look at what's actually out there, you discretize it, and then, well, you can sort of apply neural networks to that and develop theory for it. So I think this is a great place, like for mathematicians or people who want to do theory, to maybe gain some more insights into neural networks, not only in this application, but more generally maybe. Okay, so yeah, with this plug, let me end the talk. Thank you.
Thank you very much, Gerald.
I have a question regarding the analogy to generative AI, where we know that these kind of models tend to hallucinate sometimes, right? Creating images with people having 6 fingers on one hand and so on. Is there a danger in this application scenario as well that you end up with totally unphysical solutions? Or, I mean, the last comments that you made about the well-defined mapping and also the prompt, which is kind of the initial state, which is more well-behaved, is this kind of ensuring that you always kind of stay within physical, meaningful solutions?
I mean, well, in general, there's never going to be any guarantee, right? So yes, these things might hallucinate, probably they do. I think for these applications in fluid dynamics specifically, it just turns out the statistics are very well behaved in some sense. They are very stable in many cases, and so maybe having many fingers corresponds, I mean, to something that actually is a discrete transformation or something that's not so well behaved, you know. Whether you have 5 or 6 fingers, maybe that's a discrete kind of channel. Whereas here, maybe it's much better behaved in some sense. Like in some sense, like this fluid dynamics, it's so bad that that's again good. You know, it's so badly unstable but it mixes so much that it actually is kind of beneficial to some extent.
Following up on this discussion, how would you even realize that it's hallucinating? Because, I mean, 5 or 6 fingers is clear. And this is maybe what I'm just asking again in different words, right? You just get another small scale thing, which is different from the true solution, but looks great. Maybe in terms of spectrum and so you could, again, you could realize.
I guess if you had a bump in the spectrum.
Right.
Might be an
that is the 6th finger, yeah.
Yeah.
Okay.
Yeah, but
yeah. Just another question. When you said the law, you mean the probability distribution?
Yeah, exactly. So the probability distribution on this very high dimensional.
Yeah, I know that French people call it la loi as a probability distribution, but I was not aware that it's used in other languages. Yeah. Okay.
Yeah.
Okay, but it's clear. Yeah.
I mean, I'm Swiss, so maybe we are too French. I don't know.
Yeah.
Okay. The question here.
So what? From what I understand, the model can learn the physics quite well, like the diffusion model. But it's hard because it's very unstable. It's hard to know exactly what the flow would look like at the end because you have a very specific sample, right? So my question is, now you have a very good and accurate model to predict what is likely, like what scenario is likely, like physically. And did your team try to give a small portion of the flow and condition it with this small portion, and say, can you recover the most likely? So you condition the diffusion model, and you say like, this is one part of the flow, and try to find the rest of the flow that is the most likely knowing this information.
So I see what you're asking. We haven't done that. I think there's some other groups that have tried something in this direction. I mean, usually I guess they phrase it in terms of Bayesian inverse problems.
Yeah, exactly.
Trying to estimate these posteriors.
So actually our team are doing this exactly. So it's very interesting because you don't need to train anything and you can just formulate as an inverse problem and you just say, oh, we know this little part and then you can find the rest basically.
I think this is a really great application. Yeah, we haven't tried it.
Okay.
Thank you. Last question, Sven, please.
Okay.
I have two questions, both of which I'm happy also to discuss offline if we don't have time. So my first question is the following. So as you said, from a statistical point of view, there are two very different formulations, right? Because one is framed as regression, and there one is trying to, let's say, learn the conditional mean given your input. And the other one is like a joint density estimation that afterwards you're conditioning. So you're really trying to learn the probability. So I'm just rephrasing what you said. But then in a way, one could then try to do the sanity check of running the probabilistic method in your words and trying to say, okay, what is the conditional mean of my generative distributions? Does it actually kill the higher order feature? So this is my, right. So you recover again the smooth.
Yeah, exactly.
And my second question is related to that because you said that the energy, or was it called energy spectrum? Sorry if my terminology is off. Is well predicted, but somehow still the eigenvectors are maybe off. The UK hats.
Yeah, right. So it's basically the phase. The energy spectrum takes out the phase, and the phase tells you where exactly these small scale details are located. Like if you shift them a little bit to the right or left.
Yeah. So are these spectra well understood from a theoretical point of view, and is it kind of does it coincide?
So I mean, we compared the ground truth in our case with the numerical solver. So yes, I mean for this case it's fine. Are they well understood? I think in fluid dynamics nothing is well understood. So.
Okay, thank you very much. So let's thank our speaker again. I would like to invite Bill McCall to tell us a bit about the Lagrange Center, and then please stay here for the group photo.
On behalf of Huawei, I'd just like to welcome you all here. My colleague Shangling, who's the director of the Lagrange Center, unfortunately is on a business trip. So I'm the director of the main committee within Huawei that funds basic research all across the world, and Lagrange Center was one of the first major activities that we embarked on roughly 5 years ago. So I don't know how much all of you know about Huawei or Lagrange Center, but clearly it's an organization that funds meetings like this one. So maybe just want to say just very briefly a few words about basic research and Huawei. So Huawei, I'm sure you all know, is one of the world's biggest technology companies. We're active in pretty much every area of computing, developing chips, AI systems, communications technologies, smartphones, etc., etc. So as a company, we're very much a research and innovation-driven company, and that's reflected in the amount of money that we spend worldwide on research centers, labs, and academic cooperation. So here in Europe alone, we have somewhere between 25 and 30 different research centers spread all over Europe. We also have research centers in Canada and in other parts of Asia, and of course a lot in China. But one of the key strategic priorities for the company is basic research on a very broad spectrum So the committee that I currently chair, it's called the Computer Systems Theory and Technology Committee. But the Lagrange Center here is very closely aligned with that in that we fund a lot of basic mathematical research, quite often in partnership with academic colleagues in different countries. We also do a lot of theoretical computer science, foundations of AI, statistics, all of these areas, some of which are represented at this particular meeting. So what I would like to do is if you're in contact with Huawei and its, for example, Lagrange Center, the number of colleagues here at this meeting who work here in the Lagrange Center. So if your basic research, mathematical research, theoretical research could be something that might benefit from partnership with any of our research groups, whether it be in Paris or elsewhere in Europe, for example. Certainly would want to encourage you to talk to people and see whether that could be a win-win, as we say. So I'm based in Zurich. I'm the vice president of the research center there. So I've sort of multiple roles. I lead a large research lab in Zurich, but Shangling obviously is here in Paris. We also have another one of the directors in London. So it's, although Huawei is a Chinese company, we're very active all across Europe in developing academic partnerships in areas of mathematics, as I say, mathematics, AI, theoretical computer science, and so on. And so I hope you have a great meeting. I just wanted to say hello and to maybe just shed some light on why this kind of meeting is taking place. It's part of a much broader initiative that we started maybe 5 or 6 years ago, around the time that this Lagrange Center was first set up. And we have, I guess, one indicator of the kind of the seriousness with which we pursue these kinds of activities. So another one of my colleagues here in the Lagrange Center, Laurent Laforgue, a Fields medalist. He now works here for Huawei in the Lagrange Center. So very much we take mathematics and fundamental theory as a real priority, and we're always looking for academic partners to continue to build our relationship with. So I hope you have a successful meeting, and as I say, if you want to develop a relationship more, then certainly reach out to any of the people that work in those areas. So that was all I wanted to say.
Thank you very much, Bill. And I think there's a group photo now, if I understood correctly. So we should probably all...
chair this session. And I'm going to follow Helmut's example in keeping the introductions light. So what I'm going to do is I'm taking the liberty, being myself from Vienna, I'll introduce the speakers by pointing out their connection to Vienna, which with Ruediger Urbanke is super simple because he actually did his engineering degree back then at our university in Vienna before he took off to the US and eventually ended up in Switzerland at EPFL, where he's still now. He's best known for his work on error correcting codes, LDPC codes, and I take it from the title that he's going to explain to us how to transfer that knowledge to the quantum setting. Ruediger.
Thank you so much, Gerrit, for the nice introduction. Thanks a lot for inviting me. It's fantastic to be here. And I'm slightly nervous because my previous advisor is in the room. So, and I know he's very critical. So, we'll have to see. Good. Okay. We had, in the morning, we had some amazing talks about, basically physical process, how to simulate physical processes. My aim will be to talk about quantum and quantum error correction, but my aim is to take the physics out of it, okay? And to explain everything classical because my background is classical and, it can be quite a daunting task to work on quantum error correction, but I want to show you that, modulo a few minor details that perhaps in the beginning are not so important. There's a very, very simple picture. If you know classical coding, you can right away work on it, and there's really not much else that you need to know. So, but in order to get there, I need to tell you a little bit about classical error correction. And so let me just give you the most simple picture. So we're talking about transmitting bits. So let's assume you have a block of k bits. That's the information you want to transmit. And how do you typically do this? Well, in modern systems, you hit this with what's called an encoding matrix. So everything is binary. So it's k, but it's a little bit wider. So you expand the information and you get what's called a code word that's length n, and n is typically larger than k. And so, if you now put in the information that you want, then you will get from that the code word by just this matrix multiplication. Now, it's convenient to extend these bits a little bit and to add so that this vector is also length n, and then to also extend the matrix, so it's a full rank n by n matrix. And so, of course, the picture will be the same, but now, since we have this matrix, and this matrix typically, which I should say, this part of the matrix up here is called the generator matrix here. And so if you now invert this matrix, then you get the matrix here on the right, which allows you to go backwards. And in particular, this part of the matrix will be important, and that's called the parity check matrix. Okay, so it's just this part that connects this to the part here. Okay, so if we have just the code word itself, if I again, hit it with the matrix, nothing will happen. I just go backwards. But of course, transmission is not about error-free communication. It's about communication with errors, with a channel that introduces errors. And so in general, you're not just going to have the code word, but you're going to also have an error word in here, right? So you have some errors here. And in the simplest settings, it's called the binary symmetric channel. Simply this, you will have ones at certain positions. And typically the errors in the simplest setting are just IID with some probability P. And let's say think of P as whatever, 1%, 5%, 10%, whatever the error probability might be. And so if you now go backwards, what will happen? Well, if you add the two, you get now, in general, a received word which is not equal to the original code word, right? And you want to map it back to the actual information that you had here. So if you map it back, and we call, let's say, X the original code word, Y is the received word, E is the error, then what you will see is that this part here will be a mixture of whatever the code word was and the error, so you cannot just go and read the information back. But this part here was originally 0, so whatever you see here, right, only depends on the part here. And in particular, since the original parity check part here that we had was set up in such a way that this times the code word itself was equal to 0, that was the original setup, whatever we have here now only depends on the error. Okay, so what we're seeing here only depends on the error, And so that will be our clue for decoding. And this part is called the syndrome. So the syndrome is just the H times the received word, which is the same, the H times Y, because it doesn't matter, because the code word itself times the matrix is 0. So our task will be, we have given this syndrome here, right? And we're trying to figure out what the information originally was here, or equivalent, we're trying to figure out what the error is. Okay, now, maybe just for future reference, it's very easy to figure out, at least a bound on the capacity, how much information we possibly can transmit. Why? Well, let's just look here, right? We have here n bits of information. So the entropy is at most n here. Now, if we want to be able to decode with high probability, then we should be able to figure out not only what the code word was, but the code word were k bits of information, but we also need to figure out what the error was, okay? Because once we know one, we know both, because we have actually the received word here. And so this means we have the n, okay, should better be bigger than the k, plus the entropy that comes from noise. And the entropy comes from noise is n times the binary entropy function of the noise, of the bitwise noise itself. And so if you just rearrange it, you see this will mean that k over n, which is the rate, how many bits per of information you can transmit per bit of the code itself, that this must be less than 1 minus the binary entropy function. And it turns out that that's indeed the capacity of this channel. So we are trying to transmit as close as possible to this particular rate here, and hopefully can do this. Okay, so what kind of schemes have people come up with? Well, it all started with a person called Hamming, who started coming up with these matrices. Remember, we have two: the generator matrix, getting from the information to the code word, and the parity check matrix that we use to compute the syndrome. And, he wrote down some very simple ones, such things. And interesting enough, he wasn't actually interested in information transmission. He was actually interested in computation and reliable computation. This was a time where you had circuits that were built with, large with large devices, relays that weren't very reliable, and he wanted to make these circuits reliable, and that was his motivation. And so he wrote this paper in 1950, very shortly after Shannon set up, what's now called information theory. And if you look at this, this is almost exactly 75 years, from date now. So, it goes back quite a while. And so he can be, widely seen as the founder of what's now called error correcting codes. Okay, now, of course, these were very simple codes. This is not what you use in your cell phone. So what are the kind of things that you use in your cell phone? This looked like something like this. So here would be the information word. Each of them is a 0 or 1. This is an encoding, just a graphical model of the encoding of what's called this parity check matrix. Okay, so one such check just checks these particular bits that it's connected to. And so you get the received word, which is a noisy version of the code word that you have here. Okay, so code words are those that fulfill all these parity check equations here. And then you get the received word. You compute from this received word the syndrome. In the graphical model, the syndrome, you can just connect it here. And now we have a graphical model, and we use message passing, very similar to the message passing that we heard in the morning today already. I think Philip talked about it. But, essentially, all that's machine learning, stochastic gradient, all of this is exactly the kind of message passing that you have here. So you start with information, you start with the information that's on this part here, and you're trying to recover from this information the bits or the bits that you have here. You run it, and if you're lucky, it will converge and will give you the actual error word. Okay, so this is what's called LDBC codes. Now, these codes are exactly what you have in all your cell phones and any single device that you might use for communication. The only difference is that I drew here a graph that is, whatever, 15 long. What you have in your cell phone might be, thousands or might even be millions. Or if you're talking about optical communications, this might be billions or even much more, okay? So, but it looks exactly like this. And the important thing is that the graph that you have here is sparse, okay? So that's what makes things work. That's why it's called low density parity check codes, because this graph here is sparse. Now, in general, if you do this, you're trying basically an optimization problem here. You're trying to figure out what's the most likely word that corresponds to these syndromes here. And in general, you might get stuck in local minima, it depends on the graph, etc. Now, one way to get rid of these local minima is to take exactly this graph and replicate it several times, then connect it locally. So you keep the local structure the same, but you make out of it a chain. And if you do that, then you use a physical effect, which is called nucleation. It's exactly the same thing that if you ever seen this cool experiment where you have a super cool water bottle that you put in a fridge, it's actually below 0 degrees. But if you don't shake it and the water bottle is very clean, it can actually be below 0 degrees and not been frozen. But if you then take it out of the fridge, you shake it or you put a seed in there, you will see that the water bottle freezes instantaneously. And exactly the same effect happens in this if you take this particular structure here. And through this structure here, you can actually make sure that you don't get stuck in local minima. And such graphical models will actually, at least in the large limit, be guaranteed to get to what's called the ground state and will give you optimum decoding. Okay, so summary. This is exactly what's used in every single communication system that you have. This is an even slightly nicer version, but it's a little bit esoteric, so it's not really, there's only a few devices that use this kind of thing. And, whom do we have to thank for all of this? It's, of course, Bob Gallagher, who, in many, many, many years ago, 40 years ago? More. 68, no, 80, no, yeah. 62 years, okay, thank you. Okay, came up with it. He was way ahead of his time. It wasn't possible to implement them actually at that time, but that's essentially what we're using. Okay, now, the story doesn't quite end here. There's some very nice other versions. One is called polar codes. So again, we're always trying to build this generator or parity check matrix. And the question is, how do we do it? In polar codes, this is based on a small matrix, this 1, 0, 1, 1. And then what you see here is just a Kronecker product. So if you look at these 4 by 4, that's just 1 times the Kronecker product of this one. If you look at the, even this, whatever, you go out always by a factor 2, 8 by 8, etc. It's just Kronecker products of the same matrix here. And so now the question is, can you build a code out of this by picking particular rows out of this matrix? And indeed, you can do this. If you look at the ith component in here, and you write down the I in the binary expansion, then it turns out that there's a certain procedure that you need to do. It's not important right now what this is. It's basically, it corresponds to either taking a repetition of 2 bits or taking an XOR of 2 bits. And one of them will make things more reliable, and the other one will make things less reliable. And if you do this according to this expansion here, so you start, let's say, with a 1, you first make it more reliable, then less reliable, then more reliable, less reliable, whatever the expansion here is, and you compute this for a long enough sequence, then it turns out that this parameter, which depends, it depends on the original channel, and there's always a parameter between 0 and 1, will either converge to 0 or will converge to 1. So it means it's then a channel that's either super reliable or super unreliable. And so it turns out that the way to build a code is that you take the H, okay, this matrix H, just to contain those i's in here that have a very large, what's called Bhattacharya constant. So these are very unreliable. But these are the second class of codes that you now these days find in commercial applications. And since we're at the Huawei Center, it was actually Huawei who pushed very much these codes based on the amazing invention of Arikan, but it was actually Huawei who was a champion of that technology. Okay, and so the final class of codes I want to talk about are called Reed-Muller codes. Again, exactly the same matrix, but now we pick them a little bit differently. Again, we expand them. Now look at this. There's a weight of the expansion, okay? And if you look at the weight of this expansion here, and you look at the weight of the expansion here, you will find out, again, takes a few minutes to figure this out, that they're actually related. The weight here is actually 2 to the weight that you have here in general, okay? Just turns out like this because the matrix have this nice property. And so for the Reed-Muller codes, which go back to the 50s, you pick it slightly differently. Rather than picking according to Bhattacharya constant, you pick those rows that have very low weight. Okay, that's how you pick them. And it turns out that these codes are actually even nicer. They achieve capacity universally, means it doesn't matter what the channel is, as long as the capacity of the channel supports the transmission. This code will do it. So it's not just this, it also has almost optimal finite length behavior, which is, quite amazing. There's only one little downside, okay, we don't really have an efficient decoder, okay? Small little practical problem, but that's kind of the dream, okay? So to getting there would be really kind of the dream to use. Okay, so let me just skip maybe this. This is just a very nice paper that describes how to get it. And so I need just one extra ingredient from classical communication. So right now we have talked about point-to-point, okay? So the very simple point-to-point channels, bits go in, bits go out. The only thing that can happen is a certain bit flip potentially. And I've told you about the kind of 3 most common codes that are actually used. And so now to complete the picture, I need to tell you about a slightly more complicated transmission scenario, and that's what's called the multi-axis channel. So multi-axis channel is also something very classical. It's when not just a single entity communicates, but if several of them. So think of wireless, for example, you have a base station, many people connect to the same base station. It's a very common transmission scenario. And so in the simplest case, you have, let's say, 2 users. They all want to transmit something. And so, but they all kind of use the same channel. And there are, of course, many, many possible channel models. It could be, something where maybe the bits get added together XOR, etc. Many possible models. The model that we need here is actually the simplest possible. It almost isn't multi-axis at all. You still have these 2 channels. They're separated. The only thing that happens is that you just as before and you add noise. And the only difference to before is that this noise is correlated. Okay, so whether or not a bit gets flipped here or a bit gets flipped here, in general is correlated according to these probabilities. So P0 means that at some position none of them gets flipped. P1 means that this gets flipped but not this. P2 means that this gets flipped but not this. And P12 means that both of them get flipped. Okay, and in general, P12 is not just the product of the other 2. Okay, so in general, it's more complicated. So these 2 things are in general dependent and not independent. And then you just receive this, right? Okay, and so now again you want to find out what the code words were, and you can use the same techniques as before and use for each of them a code. You have these 2 syndromes here, and you would do the decoding. Okay. Now the question is, how good can you do for this? How well can you do it? Before, and I told you that for the BC, the capacity is 1 minus h of p. There's just a number. Now you have 2 possibilities, right? Because you have a rate here and you have a rate here. So you have a 2-dimensional picture here, and there will be some maximum here. There's potentially some maximum here. But due to the correlation in general, this is not just the product region. Okay, so in general, you get this pentagon here. And so I just wrote you down what these quantities are in terms of mutual information. Doesn't matter so much for us exactly what they are, but the important thing is that in general, you get a pentagon here. And if you make it specific for our case, I wrote you down what these expressions are in terms of the entropies, etc. Okay, so that's the task of the multi-access channel. And, of course, people have looked at that for a long time. And it turns out that for this channel, you can use exactly all the same techniques that I described to you, okay? LDBC codes, polar codes, Reed-Muller codes, we'll still talk a little bit about it, but in principle, very, very similar techniques than what we had talked about before and will work. Okay, so now we get to quantum error correction. That's after all the topic, okay? So in principle, a priori, it's not clear at all why you should be able to do quantum error correction. So what are we even talking about? Well, for example, in the 50s, when people started building the circuits, I told you that Hamming was concerned about reliable classical circuits, right? Because he had ANDs and ORs and NOTs gates, but these gates weren't very reliable. And if you want to build larger and larger communication, it wasn't even clear whether or not you could scale the number of gates and do a series computation and be reasonably sure that at the end the correct thing came out, okay? And so people were quite worried, and that's why they introduced error correcting codes. And maybe at the end I get back to this particular picture, okay? Now, for quantum computation, it's the same thing, but even much more serious in the sense that, quantum systems, when you build them, there's something called decoherence. And so if you want to build something serious or a circuit that computes actual, useful things, you need to make reasonably long circuits. And typically systems will not stay coherent for long enough so that you can be reasonably sure that that the output actually has anything to do with what you want to compute. So you need, again, quantum error correction. And so, but the only problem is that in quantum, things are not in standard computation. The standard unit is a bit. It's a 0 and a 1, and that fits exactly what we talked about. But in quantum, in general, the state of a system is a vector, a very high-dimensional vector, right? So if you typically have n bits, the vector is in 2 to the n dimension, is a 2 to the n dimensional vector, complex vector, and so it's in particular a vector of norm 1, so there's nothing discrete in the vector itself, and so it's completely unclear how you could use a priori error correction, okay? Now, fortunately, what do you need to use error correction? You need kind of to quantize things. You need to get back to things like something discrete. Now, unfortunately, it's called quantum, okay? And there's a reason it's called quantum, because there's actually also a quantization happening, right? So even though the state itself is a vector, and so when the system evolves, the vector might just move a little bit, okay? Once you do a measurement, which is exactly the syndrome measurements that you do when you do error correction, the measurement itself forces the system to become quantized. So meaning a priori, the system is continuous, but once you do the measurements, the system will become discrete and we go back to a discrete system. Okay, so there's kind of a miracle. First, it's bad because it's a vector, but due to the properties of the quantum measurement, things become quantized and you get back to something discrete. So, there's hope, and people, smart people have figured this out about 30 years ago, that you can actually use quantum error correction. And so the question is now, what does it look like? And my claim is that, it's extremely simple, okay? It looks exactly like this, okay? So I'll just make a few caveats. There's one important point. But if you know how to code over this, okay, you're already halfway there. There's just a few minor restrictions. The biggest one that you need to know right away is the following. You cannot just use any codes you want, okay? If you were free to use any codes you want, we would have solved this, 30 years ago, right? And practically 20 years ago with exactly the systems that I described. We know how to do this asymptotically, capacity, finite length, everything. Unfortunately, there's this extra constraint. So it means these codes that you can use here cannot just be any codes, but they have to fulfill, some kind of orthogonality conditions themselves. And that comes from the measurement process. These, what's called, what I had called here the syndrome measurements here,
these are observables or stabilizers, what they're called in quantum. In order to be able to do these measurements on the quantum system, and that you can do the measurements all at the same time, these measurements have to be what's called compatible, and that's the condition that you can all observe them at the same time. These measurements cannot just somehow interfere with themselves. Okay, so that's a condition that you have. Okay, so the challenge now is basically finding codes that do all the things we wanted to do beforehand, but also have this extra condition that we have here. Okay, nevertheless, I claim that this is a quite nice picture because this is, if you ever do communication or information theory coding, that's something that we are very much familiar with. People have thought about it for a long time. They kind of know what these things mean. And so this picture in particular about the transmission is a very nice picture to have in mind. And then you only have to worry about one extra thing, and this is the condition here. Okay? So now people have constructed codes, and I'll get back to it for quantum for a long while. They typically don't think about it in terms of this picture, but if I embed it in our picture, they typically try to transmit at a point here, which basically means you just decode this independently and this independently, or perhaps some of the schemes look more like this. They get kind of a point up here, which means you first kind of decode one, then once you know that, this tells you something about the noise in here, and then you decode the other one. Okay, it's called successive decoding. Okay, so what have people kind of thought about in quantum? Well, the first people who figured out that you can actually use quantum codes, that's pretty much exactly 30 years ago. Calderbank, Shor, and Steen, and were the pioneers of this. And so what kind of codes did they come up with? Well, kind of the equivalent of these Hamming codes. And, it's not just because these are kind of schemes, but some of them are actually built on Hamming codes. And, I'm not going to go through now what exactly this circuit means, but you can see these are kind of small circuits. And, if you stare long enough, you'll actually see a Hamming code in there. Okay, so these were the first ones that they came up with. Of course, this is not asymptotic. You're not going to achieve capacity with things like this, but still, they allow you some correction of errors in, say, for a quantum circuit. Okay. Now, what about could you use LBC or spatially coupled codes? Well, in principle, you can, right? But you have this extra condition here. And so, let's assume for code 1, this is one parity check here. Let's assume for code 2, you have a parity check here. Now, these parity checks have to be orthogonal, so it means that the number of positions where they're the same, where they line up, has to be even. That's exactly what it means that the inner product is 0. So this means it could be 0, or it could be 2 or 4. Now, they cannot all be, independent, because it would mean they completely check independent bits, and that would be a terrible code. So there has to be some overlap. So, let's assume, if there's an overlap, then at least 2 have to overlap. And if that's the case, then you can see that, through the channel here, which is the correlation here in the graphical model, you get a loop, and the loop is very small. Okay, these are loops of 4. And if you ever done message passing, you know that the one thing you don't want to have are very small loops. Okay, so again, this is not the end of the world. People have thought about it. There is a few works, as you can see, where people have, figured out how to improve this. All kinds of works on the decoding algorithm, on tweaks, etc., to get, to get around this problem. But it is kind of still an annoying problem to have. Okay, what about polar codes? Well, polar codes, remember, you picked. So this matrix has the curious another property that it's actually an involution. E squared is actually equal to the identity. So if you pick an I, then it means the only thing you should worry about is if you include somewhere in the H1, let's say this, you don't want that row to be, let's say, in the H2. Well, okay, this is a row, this is a column. You say, let's not worry about the columns. But it turns out that this column also appears here. Namely, if this is I, this thing is the same as this thing, which appears at n minus I minus R1. Okay, just again, through to the structure of the code. So what does this mean? if for one of the codes you include this, then what Reed-Miller codes. So again, this is the picture. You have the quantum, you have the multi-axis channel. We already know that if we're using Reed-Miller codes, there's no problem with compatibility. So the measurements are all fine. So this extra condition is not a problem at all. And so the question is now, how do Reed-Miller codes behave if you don't just use them for point-to-point channels, but we actually use them on multi-axis channel? And so the point is, if you just use the point here, then you could basically split it up in two independent channels, and you can just use the result about Reed-Miller codes and you're done, okay? And so that wouldn't be any problem. But if you want to be a little bit more ambitious and you want to achieve a point that's that has maximum sum rate, maybe the point here or a point in general on what's called the dominant phase, then, these two codes are actually interacting. You cannot just decode one and then the other one. You have to decode them jointly. And then it's not so clear that they actually achieve capacity. Okay, and that's what we looked into. So it turns out that this can be done. These are the conditions the standard conditions of the capacity region that I showed you beforehand. But it turns out that there's one extra condition due to the fact that you're using in both channels Reed-Miller codes, not so important what this condition is. In some cases, this condition is outside and makes no difference. In some cases, this condition, depending on the channel, will bite and will not allow you to transmit in certain region here. So what is the point of transmitting in, on this point here that I showed you? Why do we insist to transmit on this point here and not, for example, here? Well, the nice thing is if we're transmitting at a point here, then everything right now I told you was if you know exactly the channel model. If you know exactly the channel model, then you build in exactly a code, and potentially, if the code is long enough, you can achieve capacity. But very often in practice, you actually don't know, there's some uncertainty about the channel itself, right? You might not know beforehand, either because maybe you cannot measure it, or because there might be a whole variety of channel conditions, and you don't know beforehand what the channel condition will be. Right? And so in these cases, you would like actually to have some kind of universality property. So you would like to know that given all this set of channels, let's assume they all have at least a certain capacity, okay? Maybe they all have the same, or at least there's a minimum capacity. Can you construct a code that's universally good? And so it turns out that if you construct a code that's somewhere on the point here, then it doesn't matter so much, if this goes a little bit up and this goes a little bit up in here. The only thing that matters is that what this 45-degree line is, and this point might be a little bit higher up, or this point might be a little bit down. And so the actual parameters, there's a whole range of parameters in which you can actually do the transmission, and you will be fine. Okay, so we know now that for quantum channels, we kind of have universal codes, at least in the asymptotic setting, that allow us to get close to capacity. And this is just to show that this is without universality. That's the region you can do here. You see that there's a whole region for which you can actually achieve the capacity. Okay, so now I told you that this picture about the multi-axis channel is a nice picture because you don't need to know anything about quantum, okay? I mean, the only thing that the extra condition from classical one was this condition about that the inner product between the two H matrices had to be equal to 0. Right? And so if you know classical coding, that's it, okay? You can go ahead and try to build codes. However, there are some extra conditions if you want to use that, for example, for a quantum computer, that if you ever want to get that into an actual product, you should be, eventually aware of. And, there's some extra conditions or extra properties that this code should have. Now, I think the attitude right now should be is that, we are not close to actually having a quantum computer, right? I mean, it will still take a while. I mean, there's lots of progress. But, until you actually have a quantum computer with large enough number of bits and, allow you transmission, we'll probably still have 10 years, 20 years, something like that. So we can still, work a little bit. And the way that progress was done for coding in classical was not to right away focus on all the little issues that codes had to have, right? Because in your cell phone, the codes you have, they also have to have a lot of other properties, right? I mean, the codes that are in your cell phone, they're not just at a single channel with a single rate, right? They're literally hundreds of codes with hundreds of rates. And they all have to be compatible, and they all have to be the same hardware, and they have to run with, very small energies, right? I mean, for example, if you look at optical, you have a chip that has maybe 50 watts or something like that. And it has to has to decode maybe something like rates of 100 gigabits per second, right? So there's all kinds of other constraints come in. And, for some of the applications, you might need very short packets because you just want to send maybe an acknowledgement and you don't want maybe these asymptotic rates, etc. Okay? But the way coding progressed in classical one over these 75 years was that people first ignored all these constraints, thought about asymptotically how to do it. And then once you know how to do it, you go back and you look at the finite length and you look at the complexity and you look at the energy and you look at all these things, okay? And so I think the attitude for us should be the same. Let's first try to find codes that work in principle to the limits we can do, and then let's go back and add some of these constraints that might be important or will be important in practice. But if we try to do this right away from the beginning, I think it's very difficult to make progress. So what is one of the constraints that you still have? Okay, so I told you about that in classical circuits, people were originally concerned about that these individual components weren't reliable. And so that if you now build a circuit that had hundreds or thousands or millions or even many more individual gates, that eventually the output would be nonsense. And so very early on, people worried about how to build more reliable gates. And so the idea was that you could use several of such gates to build out of several such gates a virtual, more reliable, for example, NOT gate. Okay, and so Van Neumann was, for example, the first one who found something which is called the threshold theorem, which showed that as long as you had gates, individual gates, that were better than a certain probability of error, okay, then by putting several of them together and doing some extra logic, you could create a virtual NOT gate that was more reliable, okay? And once you could do this, you could iterate the process and basically get arbitrarily reliable gates out of a single, non-reliable gate. Okay, it's not quite as trivial because, if each of them fails, let's say with some probability here, well, what's the chance that one of them fails? Well, roughly, let's say 3 times as much. But if you can correct one of them, then you get kind of 3 times the probability. But if you can correct one of them, you kind of compare 3 times the probability with the probability squared. Okay, so that's fine. However, you also have to worry about this part here, right? This part here itself will have gates in there. And so it's not entirely clear how do you build this thing so that at the end you get something more reliable. But people managed. And so here you see that the structure is very simple, right? You want to build a NOT gate, you just take 3 or 5 or 7 NOT gates and you take a majority, and that's again a NOT gate that's more reliable. But in quantum, it's not quite as simple. Okay, so there are also basic gates that are universal for doing any compute. But for these gates, in general, you cannot just put them together in the same fashion, okay? Or at least if you want to do this together with some kind of code, that's just a repetition code, then you need that this code has some other properties, and this property is called transversality, okay? So there's some other structural property that you want this code to have if you want to use it for this kind of purposes in order to build more reliable gates out of this. So that's an extra constraint you might want to have. Another, not constraint, but opportunity is the picture I showed you was correct. And if you build codes like this, they will work, okay? However, in quantum, you have another quirk. And the quirk you have is that if you look again at this, you're actually not trying to recover this exactly, okay? It's actually enough to recover this up to an element of H2. So you don't worry, or you don't care if you get this or you get this plus any element of the subspace H2. And in the same way, you don't worry or don't care that you actually recover this, but it's only this up to a subspace of H1. Okay, so this is what's called degeneracy. It's something that I don't think we actually have in classical communication. I've not seen a problem where we have this. What does this mean? It means, if you don't actually need to decode exactly, but you just need to decode to a subspace, then you should actually be able to do slightly better, okay? Because you have some extra degrees of freedom. And so the actual capacity for many channels is actually not exactly known. What I showed you before and is just a bound. For some channels, we know that that's exactly the best thing you can do. For some other ones, we know you can potentially do better. And so if you really want to squeeze the last bit out, you should also find decoding schemes and codes which can take advantage of this kind of degeneracy, and potentially you can do even better. Okay? And so what's my last message? If you're into classical communication and you like coding, okay, there's a very easy way to get into it. All you need to know is the multi-axis channel plus this one extra condition, and there's plenty of open questions, okay? Lots of capacities are not known. There are very few efficient, really, decoding schemes known, etc. So plenty of opportunities. And then, of course, there are more subtle versions in there. But I think right now is a good time to get into quantum error correction coding. Okay, you still have about 10, 20 years. That's about an academic career. Okay, and then you can hand it off to someone else. Okay, thank you.
Thank you, Ruediger. Franz.
Ruediger, you emphasized read-Muller codes in your talk, but then you said in the beginning that there are no efficient decoding schemes known. So in the quantum regime, is this still so, or?
So there are decoding schemes known, but they don't bring it all the way to capacity. Okay.
Okay.
So that's yet another, I think, nice open problem. Okay.
Okay.
So if you're looking for a problem to work on, my advice is don't work on that, because a lot of people have looked at that. It's not so easy. But I think this would be a real breakthrough, because kind of these are the ultimate codes. Okay. So we know, I only talked about capacity and so on, but we know much more. We know like the finite length performance. We know like the finite length behavior, and we know that they're very close to that. Okay. And for example, Marco has worked on these kind of things. So, I think there's a promise. There's a very nice promise there. Yeah. But, there's still something to be solved.
Thank you.
Further questions? Okay.
One quick question. So the extra condition that you get for the Mac, is this because you use read-Muller codes, or is this inherent?
No, it's because whenever you use the same codes in both, it's something because structurally you have the same.
Could you lift it?
Yes. Maybe. So if you take like products of these codes, you can make it better. But that's another.
Maybe one more if I have time. Yeah. Can you give one example in which, when you use the extra condition that you need to decode X1 only up to the subspace H2 and vice versa, this gives you better rates?
Yes, so that it is, it depends on the parameters. If you look at these 4 parameters, there's a set of parameters.
So ready for BSc, there is a set.
Yeah, so there's whatever. You need to find the right correlation. And we know this because what you can do is you can kind of take this tuple and do some kind of pre-coding, and then you get a new, channel with different ones. You lose some rate because you use some pre-coding, you get a different channel. Then you can use again this bound, and sometimes when you do that, you get better rates with the hashing bound than the original one. So we kind of know this indirectly. Okay.
Thanks.
Further questions? I'm super curious about one detail in the rate region you showed. It looks like it can be non-convex, right?
Maybe just my drawing skills, but it should be convex, okay?
Oh, okay. Because I was wondering about whether time-sharing arguments would break down or anything.
No. It's just like where people think, but that should have been a pentagon.
I see. Also for the QMAC?
Yeah.
Okay. Yeah. Good. Okay, so let's thank Ruediger again.
Okay.
And we'll move on to the second talk, which will be given actually by Marco Mondelli. Marco's connection to Vienna is that he's affiliated with the Institute of Science and Technology, Austria, which is next to Vienna, not right in Vienna, but next to Vienna. Maybe you hate to hear that, but it's fair. And I just learned that you have been working with Ruediger in the past. Ruediger was moving away from Vienna, so you're now drifting back to Vienna. Glad about that. And we're going to hear something about privacy in learning in high dimensions. Thanks.
Yeah, so thanks a lot, Helmut, for the kind invitation. It's a pleasure to be here. So Vienna does seem to be an attractor for people that are related to this conference. So Rudy mentioned that his advisor stands here. So I was actually Rudy's student a few years ago. So I would say it's not so easy actually to give a talk after him, because of course he sets the bar very high, but nonetheless, I'll give it a try. So my background is in wireless communications, and we have been doing a lot of work together on error correcting codes. Although today I would like to tell you a different story, a story that's more related to machine learning and specifically privacy. The mathematical part I come from, and maybe this gives a shift with respect to the different talks that we've seen today. So the morning PDEs and now today error correction. This talk is going to be mostly about high dimensional probability in terms of tools that are being used. And machine learning, and generally privacy will just provide for me an excuse to analyze the dynamics of some of these algorithms. So before starting, let me give credits where credits is due. So this talk is based on work done with my fantastic student Simone, who's now at the moment is visiting USC. So he's finishing up at ISTA a PhD with me. So this is somewhat the unifying problem that I'll be talking about in the next 45 minutes or so. So the problem is the following. So you have a sensitive image X that you upload to the internet, say for example to Facebook. Then Meta uses all the stuff that's uploaded on Facebook to train the next family of the llama models, for example. So it's used to train a model here. So D is the data set, theta star are the parameters of the model, A is the algorithm that's used to train the model, P is going to be the dimension of the parameter space. Then the llama models are open, so you can actually go and actually download stuff. And so if you have access to the parameters of the model, perhaps a malicious user, say Nicolas Carlini, if you're into ML and you've been following, for example, some of his talks, can just go there and can try to find what's the image that you uploaded to the data set. Okay, and there is a huge literature on the matter. So this is the general problem that I'll be talking about. So my talk is divided into two parts. So I'm going to have a prelude, which is the first part, a little bit shorter than the second. So the prelude is going to be mostly exploratory. So what I'm going to say is that indeed, if you do ERM, then you have spurious correlation, you have spurious features. So there are problems that are indeed involved with this approach. And here I'm just going to try to understand how much you can memorize things, so how bad the adversary can hurt you. Okay, so I'm not really going to provide a solution, but I'm just going to explore how ERM does. Then in the second part, I'm going to be looking at how to defend ourselves from that, and I'm going to be resorting to probably the most widely used paradigm in the theory literature, which is differential privacy. Okay, so this is about empirical risk minimization, this first part. So here is a thought experiment. So now I train my model and I obtain my model f of dot theta star. So theta star are the parameters, say, of the llama model. Okay, the dot stands for the input that I feed in, and my model is trained until the end of time, until it interpolates all the trained data points, which is, I would say, common practice now in machine learning. Okay. Now I have access, say, to the uninformative part of the input image. So this is my input image. So this is the image of a cat in a box. So no cat was harmed while doing this experiment. This is the cat of a grad student. Now I decompose the image in two parts. So I have the cat, which is the informative part, and I have the background. Okay, and the background is uninformative. So my question is the following. I take my trained model and I feed my trained model just with the background. So I take the background and I put here, say, all zeros. Okay, and my question is whether the output is now correlated with a true label. Okay, now if life were good, the answer should be no, because I gave you no information that indeed the cat was here, but the model has seen this image before, so it could remember about that. Okay, so this is just a thought experiment. So the question is, can you recover the information in the label? Can you recover the information in the image, just having access to something that's completely uninformative? Okay. Now, something slightly less of a thought experiment, and this comes actually from Simone's internship when he was at AWS. So he looked at the following things. So say that you do an experiment with LLM, so you give a context. So for example, this is about Beyoncé's performance at the Super Bowl, so about 10 years ago. And then you feed the LLM, you feed the LLM with a corrupted context, okay, in which you remove parts of the information. So in this case, for example, you remove the actual date of the Super Bowl. Okay, and then you ask a question. And the question is about part of the data that you removed. So in this case, you ask, what day did Beyoncé release her single Formation? And actually, she released it on February 6, 2016, but you removed 6 and 2016 from the context. Okay? So here, what you would like to have is that you would like to have as an answer February, because this is what he sees in the corrupted. You definitely would not like to have February 6. Okay? Now, in this second example, so here this is a text that contains some numbers. In the corrupted context, all numbers were removed, and then a question about those numbers was asked. And then the LLM is actually able to retrieve those numbers, just because he saw them probably in some other data point. Okay, so maybe an example that's perhaps more fitting, what you could do is you take a picture of your credit card and then you remove the digits from the credit card and then you ask the LLM what are the digits in the credit card, and if it saw that just by scraping the web, say the dark web, probably it could be able to retrieve that. So that's the problem. All right, so beyond the metaphor, now after all this introduction, maybe it'll be a bit disappointing, so I'm gonna be doing supervised learning with IID datasets because I still wanna do math on this. So my data is XY and they're all IID samples from a certain data generating distribution. Then the axes have two parts, so ZI and NI. So ZI is the informative part, the part that contains the cat. NI, N stands for noise, here is the background. So this contains something that's completely relevant to the label. Okay, and I'm gonna assume that the Z and the N are statistically independent. Furthermore, the label Y is only a function of Z. Okay, so Z is the useful stuff, N is just the background, completely independent. The label only depends on the useful stuff. All right. So our goal will be to minimize the empirical risk. So as I said, for this first part of the talk, I'm going to be focusing on empirical risk minimization. So I'm going to be solving the following minimization problem here. Okay. And in particular, I'll be looking at generalized linear models. So here, the model that I will fit is a linear model in some nonlinear feature with respect to the input. Okay. And then I will focus on some specific generalized linear models, so on some specific feature maps just later. Now, the reason why I do that is that this allows mathematical tractability. So in this case, I know exactly what's the solution of gradient flow, which is something like the pseudo-inverse of the feature matrix times the labels. So this guy is just the pseudo-inverse, so it's the left inverse. The matrix phi is obtained just by packing all the features of all the samples. So it's n by p. So throughout all my talk, I'm going to have three parameters. So d is the ambient dimension, n is the number of samples, p is the number of parameters of the model. Okay? So this is the feature matrix. It has n rows because I have n samples, and each row has length p because this is the number of parameters of the model. So the feature map maps the dimension d, which is the input dimension, into the dimension p, which is the number of parameters. All right. So again, here we consider ERM at interpolation. So this is the gradient flow solution, and as long as p is bigger than n, this interpolates perfectly the training data. And we're going to be looking at some more sophisticated algorithm that have some protection against this in the second part. All right. So the problem can be formalized as follows. So now I want to recover, say, the label of the first sample, given access to a masked sample. So the masked sample does not contain anything about the Z part of the feature, which was the informative one. So that's the part of the image that corresponds to the cat, but has exactly the right noise. Okay, so I have access to this masked sample, and I have query access to my model. So I know the weights. I know the weights, and say I know the functional form of the model as well. Okay. So this was what happened during training. So this is the first element of the training set. If I plug in the model, the true image of, I get cat because I interpolate. So this is my first label. And I want to understand how does the output look like when I feed in something like that. So I remove the cat, so I remove the informative part, and I just feed the background image. All right. So if you do a little bit of calculation, not too complicated, you obtain an expression like that. So let me unpack it. So f of x1n comma theta star is the query using the spurious feature. So theta star are the parameters of the model, which I assume I have. So I'm querying the model with a mass sample. So this is equal to f of x1n comma theta star minus 1. So theta star minus 1 is the leave one out solution. So this is the solution that I would obtain if I train the model with the same data set, excluding the very first sample. Okay? So now this object is entirely independent on the label, because this does not see the first training sample during training time, and it does not see it under test. Okay? So it never sees actually the image I'm interested in. So if I only have access to this, I'm safe. I will never be able to retrieve the label. Plus an extra piece. So the extra piece contains two parts. So the first part can be related to the sensitivity. So the sensitivity is the change in prediction that happens if I add only one training sample to the process. This is because y1 is the true label, so y1 is also the output of the model if I plug in x1. So this is f of x1 comma theta star, because the model interpolates. And this is f of x1 comma theta star minus 1. So this is the output if I train the model with everything except the first sample. Okay, and this is something somewhat very classical in statistical learning theory. There is a nice paper, for example, by Bölcskei that dates almost 25 years back, where these folks connect this leave one out to the generalization. In particular, the connection is pretty easy. So if you just take the expectation over the samples, the expectation of the square of this quantity is just the generalization for the algorithm that's trained on everyone except the first sample. So that's this term here. Okay, what's the proportionality factor? The proportionality factor is something that we call the feature alignment. And it's essentially the following object. So I take the feature with respect to the first sample, I take the feature with respect to the mask sample, and I apply a projector operator. Okay, so this captures the similarity between the masked sample and the true sample in feature space, because I apply the map phi and I apply this projection operator here. Okay, so this may feel a little bit mysterious, and that's going to be the central object of our study. Just as a sanity check, this is indeed a sort of similarity, because if I plug in the same quantity here, x and x, then the feature alignment is equal to 1. That's easy to see, because the projection is equal to the projection square, and so this simplifies with the 2 norm that's at the denominator. All right. So let's still interpret this formula just for a second. So assume for the moment that this mysterious quantity, which is the feature alignment, is close to a constant. Then the covariance between the label and the output of the model with the mask sample is going to be roughly the square root of the generalization times this feature alignment. And okay, here I also have the root of the variance of y1, which you can think as a constant. So this is just a normalization thing and depends on the size of the label. You can think that that's 1, for example. Okay, so what does this formula tell us? So this formula tells us that the memorization increases with the similarity between the mask sample and the true sample. So that's reasonable. But in particular, it increases according to this specific metric that we have here. So this is the similarity in feature space. And that's mediated by the projection operator. So that wasn't so easy to guess from the start. And second of all, the memorization increases as the generalization error increases, which kind of makes sense, because if the generalization error is bad, it means I'm overfitting to the training dataset, and so I should be able to retrieve them one by one. Okay? And a similar interpretation can be obtained also for the spurious loss. So if you don't like as a performance metric the correlation, the covariance number of sample grows because I'm generalizing better. Now, the thing that's perhaps more interesting is that the test accuracy doesn't really depend much on either alpha or the choice of the activation, while the spurious accuracy does, very much in accordance with our theory. Okay, so here, for example, the red curves correspond to alpha equal to a half, and the blue curves correspond to alpha equal to a quarter. So half gives higher spurious accuracy, so the attacker is more successful because it sees a larger part of the image, a larger fraction of the image. And also the Hermit coefficients matter in the sense that using an activation that is phi2, so as only the second Hermit coefficient, leads to a spurious accuracy that's higher than phi4. Okay, so having activations that have lower order Hermit coefficients makes the lower bound bigger and also leads to a higher spurious accuracy. Okay? And the same thing, and more or less the same qualitative behavior can be seen if you try this on standard data sets, NIST and CIFAR10. Again, just in the interest of time, I'm not going to be talking about this, but we have similar results also for NTK features in which our bounds are actually tight. So in this case, we can pinpoint exactly what's the limit of this object. And also some experiments on real neural networks, such as ConvNets or ResNets, that show a similar qualitative behavior. Okay. I would also like to say something about spurious correlation. So here, the model was the following. So my data is divided in two parts. The useful part, Z, and then the background, Ni, and the useful part and the background are statistically independent, and the label only depends on the useful part. Okay, so we phrase this as a problem in which I have spurious features. The spurious features are irrelevant for the task, but they get memorized at training time if I train anti-interpolation, and I want to capture by how much can I guess the label based on having one of the backgrounds that was used at training time. A related problem that we looked recently is something that is called in the field spurious correlations. So in this case, I modeled the background as being statistically dependent on the features. Here, the prototypical example is the following. Say I train, for example, a classifier that has to discriminate a truck with a boat. Now, most boats have a blue background. So there is a statistical correlation between having a blue background and having an image of a boat. So then what I could do is that I could give the model at test time a new blue background, now with a truck. And the question is, will it classify it as a boat or not? Okay? Which is something that most models actually do. So in this case, what we are capturing is the following. So we take theta star. So theta star is always for me the parameters at convergence. So these are the trained parameters. And now I sample a new data point. Okay? But in this data point, I sampled the background and I sampled the true image from the product of the marginals. So now I destroy this correlation. So I give you a truck and I give you the truck with the background of a boat. And then I ask, what's the covariance between the output of the model and the true label? Okay, now if the covariance is 0, then this means that the trained model does not rely on spurious correlation. If it's non-zero, it does rely on them. And okay, what we do is that we give a precise characterization of this in the proportional regime, where n is proportional to d. So we do that for linear regression. We extend this to random features, and then we do some considerations on how the strength of the regularization and the covariance of the data affects this. And okay, this will appear at ICML this year. All right, so this was somewhat a prelude. So now I told you a problem, and I investigated the problem a little bit. So I told you on what does it depend on. And indeed, models learn spurious correlations and they memorize spurious feature. So how do people defend on it? So there are plenty of ways in which people can do this. Something that's, I would say, well established in the theoretical literature, it's what's called differentially private training. And I'll tell you in 1 second what I mean by that. And what I'm going to show you next is an analysis of differentially private training for a specific setup, in particular for a model of random features. All right. So this was introduced almost 20 years ago by a landmark paper by Cynthia Work et al. So this actually comes from the theoretical computer science community. So the definition of epsilon delta differential privacy is the following. So let me pick two data sets, D and D prime, and let me call them adjacent if they differ by only one training sample. Okay, so D and D prime are all the same, but one training sample changes, and that change is adversarial. So the training sample that I change can be anything. So I'm going to say that an algorithm satisfies epsilon delta differential privacy if the following thing happens. I ask whether the probability of the output of the algorithm being in a set S has to be upper bounded by e to the epsilon times the probability that the algorithm applied on the adjacent data set D prime belongs to S plus delta. So again, I just change one training sample and I ask what's the output, how does the output of the algorithm changes. Okay? In particular, I allow myself two slacks. So I allow myself an additive slack of delta and a multiplicative slack in the probability of e to the epsilon. So if epsilon is equal to 0 and delta is equal to 0, then I have perfect privacy. Because in this case, the probabilities are exactly the same. So I get an upper bound, and then by reverting the role of d and d prime, I get a lower bound. And so in this case, I have perfect privacy because the output of the algorithm for all sets S is indistinguishable, whether I trained on D or I trained on D prime. So I will never be able to recover any single data set, right? Because if I just change one and I look at what are the statistics of my weights, the statistics are exactly the same. So there's nothing I can do. Okay, so in this case, perfect privacy. If delta is 1, then no privacy because the upper bound trivializes. If epsilon is much bigger than 1, also no privacy. Okay, now in practice, I think meta uses epsilon equal to 8 and delta to be of order 1 over n. So in practice, epsilon is of order 1 and delta is usually of order 1 over n when n is the number of training samples because you want to do a union bound on them. This is the typical numbers. Okay. So how do you achieve that? So again, as I mentioned, this notion comes from the theoretical computer science community. For example, they were interested in problems like learn the mean privately or stuff like that. 10 years ago, say deep learning came, and people were interested in making differentially private versions of algorithms that are like gradient descent or its variants. So gradient descent is what? So in gradient descent, I take my loss function. So the loss function depends on my sample xi, yi. I take the gradient. Then I average this over all the training samples, and then I update my parameters. So that's GD. What's differentially private GD? So differentially private GD is the same, but with 2 tweaks. So the 2 tweaks are, well, really 3 tweaks. So the first tweak is clipping. So what I do is that I clip the per sample gradients. So I take the sample with respect to one, I take the gradient with respect to one of the samples. Then if the norm of the gradient is too large, I keep the same direction and I reduce the norm. Okay, in particular, I clip the norm to be at most this constant C-clip. Now the reason why I wish to do that is that I don't want that any gradient is too big. Because if the gradient is too big, it means that the sample that I took the gradient from becomes identifiable. Because it makes me do a very big gradient step. Here, the typical example that people, for example, give is that of a white tiger. So say I'm training a classifier that's trying to distinguish tigers from a different animal, okay, from whales, say. Okay, now most tigers are orange or reddish or something like that, but then my training data set has one single white tiger. Okay, now the white tiger is an outlier. And so every time I pass through it, I'm going to make a big gradient step because it's pretty different from all the others. So in that case, the big gradient step is what helps me identify that this was indeed part of my training data set, because this changes my dynamics a lot. So that's the first tweak. The second tweak is to add Gaussian noise. This is called also the Gaussian mechanism in the DP jargon. So I have to add noise just to reduce the dependency of the trajectory of any single training sample. Okay, and people typically use for other problem Laplace noise. That's the Laplace mechanism. But for gradient descent dynamics, it's much more common and also much easier to analyze adding Gaussian noise. Okay. Now the third tweak that's perhaps less apparent from this is that I'm going to do early stopping. So later I will compare the trajectory of the algorithm that is trained until convergence, until the end of time, until I interpolate exactly everything, against the DP algorithm that's early stopped. And I want to do early stopping because here there is a delicate trade-off that I have to hit, which is going to be probably more clear in this slide. So this slide tells you that this algorithm here is epsilon delta differentially private, as long as the variance of the noise that I add is at least this much. Okay? So this depends on delta and epsilon, in the sense that as epsilon and delta go large, the variance that I have to introduce is less. That makes sense. Because of course, if I add more noise, then my algorithm is more private. If I add less noise, my algorithm is less private. But note that sigma depends on root t. So sigma actually depends on the number of steps that I do. So if I train my algorithm for less, then it means that I have to add less noise to achieve the same privacy. Or conversely, if I add the same amount of noise, if I train for longer, then I have more opportunity to memorize my training data set. So the third tweak is that I'll have to do early stopping. Okay, so maybe here the take-home message is deep learning with differential privacy is just deep learning, but then I do gradient clipping, I do noising, so I add noise, and then I do early stopping. All right. Now, what I'm interested in is to develop a privacy utility trade-off. So what's that? So here I want to study the excess population risk, in which I compare the solution of the epsilon delta differentially private algorithm with the solution of the vanilla algorithm that doesn't have any privacy guarantee. So for example, this guy is the test error of ERM. So this is what I have considered in the first part of the talk. So here there is no privacy guarantee. This is my standard algorithm. This guy instead is the solution that I've obtained from the epsilon delta dp algorithm. Okay, so theta dp indeed satisfies epsilon delta dp by construction, because that's how I have designed my learning procedure. Now, somewhat the gap that we wanted to address in this work is that existing work typically comes from the convex optimization literature and doesn't really look at the overparameterized regime. So by overparameterized, I mean that the number of parameters of the model, so P in my notation, is typically much bigger than N and D. So the number of training samples and the number of input dimensions. So for example, this is what a typical bound for linear regression looks like. So it's something like P over N, P squared over N squared epsilon squared. So when P is large, then this becomes vacuous eventually. Now, of course, for linear regression, I realize that's not entirely fair because the number of dimensions is equal to the number of parameters of the model. So let me also look at something a bit more general. This is for GLMs and generally for convex and constraint optimization. So the typical bound looks like something like this. So the excess risk is 1 over root n, which is the parametric rate. And then I have something like root p over n. So when p is larger, then the algorithm becomes less private. Okay. And here, of course, I have a few other terms, the diameter of the optimization domain, the Lipschitz constant of the loss, stuff like that. Again, there is a pretty extensive literature on the topic, so these are just two representative meta bounds that you can read from these papers. But pretty much all these bounds tend to become vacuous when you increase the number of parameters of the model. Now, there are heuristic reasons for why this may be true and may be inevitable, in the sense that when I increase the parameter space, then of course I have many more opportunities to memorize my samples. And so in principle, I should be less private. So for example, the noise introduced by DPGD should indeed increase with the dimension of the parameter space, just because the typical size of the model is something like the root of the number of parameters. This is just, if every parameter is of order 1, and then I look at the typical L2 norm, this should be something like root p. So it kind of makes sense. So these are the parameters that I'm updating, and so the variance of the noise should indeed increase with root p. And this is actually motivated a non-trivial line of work that actually looks at lowering the subspace in which the dynamics happen. So here what these folks are doing, they're trying to find a low-dimensional subspace and restrict the dynamics there just to reduce the number of effective parameters that are updated by the model. Now here I would like to take a different perspective, and to do that, let me perhaps present you this picture that I stole from Misha Belkin's paper on double descent. Now my claim is that in the overparameterized world, or when you consider models that are vastly overparameterized, many of the traditional statistical wisdoms tend to fail and a different picture arises. So this is what I would like to show you today for DP algorithms. So this is something called double descent. So in this case, this is the usual bias variance trade-off. So the usual bias variance trade-off tells you that as I increase the number of parameters of the model, first my risk decreases because I fit, then I reach an optimum, and then I overfit because I have too many parameters. Now what Misha first and then a few other people also noticed is that if I keep doing that, Okay, my risk increases. It keeps increasing until I reach the interpolation threshold. So at this point, I have enough parameters to perfectly interpolate the data set, and then it decreases again. And this is what they call the modern interpolating regime. And this has led to a relatively rich mathematical literature into studying indeed what happens for over-parameterized model and characterizing this double descent curve analytically. So the first thing that we did was an experiment. So then we were just asking ourselves whether indeed it's true that the test accuracy deteriorates as you increase the number of parameters. So here we trained a two-layer ReLU network on NIST with DPGD, and we did a proper hyperparameter search. And what we noticed is that it's not true that as the number of parameters increases, my performance decreases. Okay, so this is what's suggested by all the previous bounds. So all the previous bounds somehow suggests that as the number of parameters grows, your bounds at some point should be bad, but that's not really true. And okay, maybe you can say, well, but perhaps you guys are not good enough engineers. So if you don't trust us, perhaps you should trust this large-scale experiment done by DeepMind people that showed the benefit of scale for differentially private training. So here they trained, I would say, at ImageNet scale, and they showed that if you do a proper hyperparameter search, then you can indeed improve performance by using larger architectures. So using tons of parameters is actually a good idea for DP training as well. But this is something that's definitely not captured by existing bounds. Okay, so maybe different approach is needed. And we're going to do that on random features. So that's exactly the same slide that I had before. So now my loss is the true label minus the random feature model. So the weights of the first layer are V, and they're fixed, Gaussian, untrained. And then the weights of the second layer are trained via ARM, or in this case, via epsilon delta DP algorithm. Now, the non-private learning dynamics was characterized in a bunch of works. So this one looked at the sharp proportional regime, and these other ones looked at various generalization in the polynomial regimes and for models that are more general than random features. And here is how our result looks like at a high level. So we look at random features. Again, there are three parameters that are interesting. So one is the input dimension, that's D. The other is P, is the number of parameters of the model, and then I have the number of samples N. Okay, I'm interested in establishing what's the excess risk, RP. So the excess risks compares the performance of non-private GD, so I just run GD until I interpolate, until the end of time, and epsilon delta DP, where I choose the parameters carefully. So I need to do a proper hyperparameter optimization, and our theory also tells you how to do that. Then, for models that are over-parameterized enough, so P at least N squared, under some technical condition that I'll elaborate in just a second, this is how the excess test risks look like. So in particular, so our paper has the fancy title, privacy for free. So here you get privacy for free when the number of samples is between D and D to the 3/2. So this is what removes these two terms from the bound. So when N is between D and D to the 3/2, this part vanishes. And in this case, I get a vanishing excess test risk as long as epsilon is of order, is at least faster than D over N. So this also allows epsilon to go to 0. So for any N that's super linear in D, then I can indeed ensure vanishing excess test risk with a perfectly private algorithm. All right. A few perks. So the bound does not depend on P. So there is no trace of P here except in the polylogarithms. So O tilde removes the logarithms from the bound just for readability. And it holds for any sufficiently over-parameterized model. So when P is much bigger than N squared. Okay, N squared is actually not right. So here I think it should be P much bigger than N. But life is tough and math is tougher. So in this over-parameterized regime, existing bounds trivialize. So we took actually the liberty of computing a bunch of them. And these indeed trivialize in this regime. So this is indeed a new result. And the technical conditions are relatively mild on the data. I just need good tails. And I need something non-trivial indeed on the activation. So I'll need that the 0th and second Hermite coefficient of the activation are equal to 0. I think this is really for technical convenience. If the paper was maybe 50 pages longer and we had other 6 months, maybe we could have left that. I think this is a challenging but solvable technical problem. All right, so I have 7 minutes. So I'm not sure I'll be able to go into the proof, but maybe let me give you 2 cartoons. So the first cartoon plots the test error of DPGD versus the test error of vanilla GD only for two-layer net. So we have already seen this. So the blue curve is just the standard GD algorithm. And then black, red, yellow corresponds to algorithms that are progressively more private. Here, what I would like you to focus on is that as the number of samples grows, the gap between DPGD and GD shrinks. So let's look, for example, at the gap between blue and black. So here it's pretty big, it's pretty big, it's pretty big, but when n is large, here it shrinks. Okay, so that's the first piece of evidence that I would like to give. So if I have more samples, and I'll clarify what more samples means, then the gap between the two diminishes. This is the second cartoon. So this is courtesy of Theo that I think in his last year of grad school decided to spend the summer trying to prove this for random features. Basically what this says is that the test loss of random feature follows a sort of staircase. So first, the random features basically learn different polynomial approximations of the target. So when the number of samples is between basically a constant and d, then I just learn constant functions, I learn nothing. Then when the number of samples is between d and d squared, so this plots log n over log d. So here this corresponds to n being between a constant and d. This corresponds to n being between d and d squared. So between d and d squared, I learn the best linear approximation of the target. Then I go down to the next piece of the staircase, and I learn the best quadratic approximation of the target. So here n is between d and d squared. So my proof works here, because I said that n is between d and d to the 3 over 2. I actually suspect that the same thing is true in much wider generality, pretty much in the generality in which this picture is true in all pieces of the staircase, except the pieces where it drops, because, I mean, their life is tougher. So what does this say? That basically I have these plateaus. So the plateau suggests that when the number of samples is between d and d squared, then I can just use theta of d samples to achieve utility, so to get good test loss. And then all the rest I can use to achieve privacy. So I can use all the remaining samples, not really to get a better test error, because I can't do that. I don't have more than d squared, so I will never get to the next part of the staircase. But I can just use them to average my results more, so that every sample becomes indistinguishable. Okay? So that's really the reason why you get privacy for free, and it's really the reason why the result is even true. I mean, perhaps what's interesting is that DPGD automatically does that. So it's not that it uses only the first d samples to get utility and then it uses the rest just to average. This is somewhat automatic in the dynamics of the algorithm. So beyond the two pictures, basically what we do is we need to get a non-asymptotic control of the whole DPGD trajectory. This is kind of a higher goal than what was set up by the previous papers, because the previous paper just cared about the solution at convergence, which for random features and for generalized linear model is a pretty nice structure, because the pseudo-inverse times the labels. So all the other papers pretty much just looked at that. In our case, I need to look at the full trajectory because I have the clipping part to take care of. So I need to make sure that my gradients are never big enough. So I need to control my gradient to out. So this is a bit more painful. Okay, so these are the three main steps. So the first idea is to go from DPGD to a certain stochastic differential equation. So to think DPGD as the Euler-Majorana discretization of an SDE. Next, I'm going to say that the SDE is controlled in a certain set. So the gradients are never too big. Okay, so I never clip. And the last part will be to analyze what happens if I add noise and if I add early stopping. Okay, so I have maybe 3 minutes, so let me say 2 words about this. So how do I see that DPGD is actually an SDE? So clipping the gradient is equivalent to clipping the loss, because instead of clipping the gradient, I can just consider a different loss, which is quadratic up to some point, that's C clip, and then is linear. Okay, so if you're a statistician, this is going to be very familiar to you, because that's the Huber loss. Okay, now, at this point, I've removed clipping, so I can write indeed DPGD as the discretization of a certain stochastic differential equation, which is something like this. So this is a Brownian motion, and it has a drift term. And the drift term depends on the clip loss. Okay, now the clip loss is pretty nasty, because, okay, it's quadratic, then it's linear. It's not so obvious how do you analyze this. The quadratic loss was indeed much nicer. So our strategy is indeed to prove that if I set up the clipping constant large enough, then the whole dynamics happens in the quadratic region of the loss. And so I can just consider the original quadratic loss. So clipping effectively never happens. And to do that, I need to set the clipping constant to be slightly faster than root p. So root p is the typical size. So root p is the typical size of the per sample gradient. So what you can show is that if you just add the log to that, then you never clip. Okay? And okay, in the interest of time, I think I'll skip this part. So you just divide this into the noiseless solution and the part that comes from the Brownian motion, and then you bound the two separately. So the part from the noiseless solution you do via leave one out analysis, in which you remove one sample at a time. And the other part is just basically a Brownian motion with an attractive drift that's given by the gradient. Okay, and you show that both parts are at most logarithmic. Okay, effect of noise and early stopping. So as I said, my dPGD dynamics is equal to a certain average. So that's the part without the noise, and then the part with the noise. Okay? Then I can also decompose the average into the solution at convergence plus the part that depends on early stopping. Okay? So the average, the noise, is responsible for this piece in the bound, d over n epsilon. Okay? Then the early stopping contributes to this other term in the bound. And this, I think, is a pretty nice part that connects well to the staircase picture, because what you can show is that there's a spectral gap in the kernel. So here I look at the kernel that comes from the random feature, and this exhibits a spectral gap in the sense that the dth eigenvalue and the d plus first eigenvalue are very far from each other. So this suggests that what's happening is the following. So at the beginning, the training loss and the test loss go all together, because I'm indeed learning. Then at some point, the test loss and the train loss start to diverge. The train loss is reduced because I'm fitting the noise. The test loss doesn't go down anymore because I don't have enough sample to reach the next part in the staircase. Remember that when n is between d and d squared, my test loss is flat. So this means that when n is, say, d to the 3 over 2, then the extra samples between d and d to the 3 over 2 don't help me in the test loss. They just overfit noise. So the moment in which I should stop is exactly here. So basically, I'm learning all the top d eigenvalues of the kernel, and when I hit the dth, then I stop learning, because the d plus first eigenvalue is too far. I will never be able to learn it in time with the sample size that I'm allotted. That's the idea. Okay, and this contributes with this part here. Again, this part is not tight because I think the results should be true when n is between d and d squared. Okay, so my time is up. So here we just had some numerical simulations. One thing that's interesting to note is that the regularization effect of the noise and early stopping is similar to ridge regression, is similar to regularization, because this is inducing indeed an effective regularization in the dynamics, and this is something that the statistician had understood over 10 years ago. One thing that's interesting is that the scaling of the parameters is correct, because here I'm plotting the test error of dPGD as a function of the number of training steps. And okay, this is a U-shaped curve in the sense that it has a minimum. So there is an optimal amount of training time. And the optimal amount of training time has exactly the same scaling that you predict from the theory, which I think is pretty nice, and you see pretty well in this picture where I collapse them according to the scaling that I predicted from the theory. And okay, finally, this is a two-dimensional plot. So I'm plotting the test error as a function of the clipping constant and the amount of iterations. So we prove what happens here, and this part is yellow, which means that the test loss is small. So this is good. So this is a good hyperparameter region. One thing that's interesting is that also aggressive clipping shouldn't be a problem, but we can't really analyze that because we're in a regime where clipping never happens. And okay, something about aggressive clipping is indeed something we're thinking about these days, and stay tuned if you're interested in that, because there are some tools that allow to analyze that as well. Okay, and with that, I'd like to conclude. So this talk presented some analytical tools to characterize certain phenomena that happens in practice when you deal with either non-private algorithms, so ERM, or differentially private algorithms. We learned a few high-level lessons, which concern the interplay between spurious feature and generalization, and that overparameterization doesn't have to be at odds with differential privacy. But perhaps most importantly, we just developed a general approach and toolset that could go beyond to say something about kernel ridge regression, about the polynomial regime, about feature learning, about aggressive clipping. And on this pretty optimistic note, I would like to thank you for your attention.
Thank you, Marco. We're accumulating a little bit of a delay, but since we have only 3 talks and not 4, I think it's fine to take 1 or 2 questions if there are. Helmut.
Thank you. Thank you, Marco. So for the double descent curve, I guess it's actually not really related much to your talk, I guess. But my question is, if you think about the Young-Barron framework, right?
Okay.
I was wondering when I saw your explanation of the double descent curve, when we have this parameter kappa, let's say it's epsilon, approximation or epsilon squared, has to be on the same order as the metric entropy, of the function class we are regressing against. I was wondering if you, sorry to make you, So, and you put here the interpolation threshold and then things start going down again. But Young-Barron tell you if you balance epsilon squared with the metric entropy, right? And if you have a function class whose metric entropy, I mean, whether you have epsilon squared doesn't matter, it's just a constant, right? I'm just, do you have a thought about how
I mean,
that would,
there are ways in which you can lift this down. For example, one thing that you can do is regularize. So epsilon delta dp effectively does this. So epsilon delta dp takes the peak and brings it down because it adds noise. Another way you can do that is via ridge regression. So if you add an L2 penalty, that also brings the peak down. Another perhaps slightly more elementary way to see the peak is that here, the number of parameters is equal to the number of samples. So in linear regression, the solution is something like the pseudo-inverse of the data matrix times the labels. So here is where the pseudo-inverse becomes ill-conditioned. Now, when you do L2 regularization or L2 penalty, then instead of the pseudo-inverse, you have pseudo-inverse plus regularization parameters times identity inverse. So that regularizes it. So now that's well-conditioned because the smallest eigenvalue is bounded away from 0. So that brings this down and brings this up.
So I guess, I mean, these double descent curves are always for specific training algorithms.
Yes, so this depends a lot on the specific training procedure that you have.
And Young-Barron tell you that should not even happen, right?
Yeah, of course, but that makes sense. So this is somewhat your fault as the algorithm designer.
Okay, thanks.
Okay, further questions? All good? Okay, so then let's thank Marco once again. And this brings us to today's last talk. The speaker will be Rémi Grubonval from INRIA ENS Lyon. Rémi seems to be one of the few truly French attendees of the workshop, and he does have a link to Vienna. He's actually on the advisory board of the Acoustic Research Institute of the Austrian Academy of Sciences, and we were talking before he was just visiting Vienna last week, right? So here we go. And Rémi will also talk about neural networks, but okay, slightly different title than what I saw in the program. There was more symmetries, but here is invariances, which is connected anyway. So looking forward to that.
Can you hear me? Yes. Okay, so thank you, Helmut, for the invitation, and thanks for the. I was looking forward for the connections to Vienna, but, which thanks. So today, what I will be talking about is the role of rescaling symmetries or invariances in neural networks, starting from the issues that they raise and trying to see how we can harness them. So this is obviously some work that I didn't do alone. So the main, most of the contributions are from Antoine, who recently defended his PhD thesis in our group, co-advised by Elisa Ricchetti and Nicolas Brisbard. He is now a postdoc at EPFL, so perhaps close to the group of Sven very soon. And in the very end, I will say a few words about the work of Sybille Marcotte, who is completing her PhD this year with together with the supervision of Gabriel Perret. So, to begin with, what are we talking about? You're probably aware that there are numerous deep networks that are used in many applications, and many of them are exploiting the so-called ReLU activation function, which shape is displayed here. And you may know that this ReLU activation function has is homogeneous, which is a property that has a direct impact in the parameterization of the corresponding networks. So when you think of a network, usually you think of a huge graph, a huge computational graph. Here's just a zoom on a single neuron that's buried in a computational graph, taking an input x to compute an output f theta of x, where theta collects all the parameters, weights, and biases on the network. And here what happens is that if for any single neuron, if you scale up all the incoming weights by a given positive scaling factor and divide the outgoing weights by the same factor, there's absolutely no effect on the input-output relation of the network. So this is something that is, both a blessing, or that could be a blessing or a curse. But for sure, what it means is that it leads to the ability to define a notion of equivalent class of parameters that are indistinguishable. I mean, that can be rescaled from one another, and so this kind of equivalence by rescaling relation leads to the equality of the functions that we implement. So what this means is that if you start, if Amit gives me a neural network and Helmut modifies it to get rescaling equivalent parameters, the two networks will lead to the same function, but if I start from these networks to do some optimization, the gradient will be different at the different parameters, so I'll have different dynamics, different trajectories, and so on. Also, if I try to compute some norms on the weights, perhaps to predict what are the Lipschitz constants, what is the regularity of the network, I'll get a different answer. And also, if I try to identify what are the significant coefficients to compare coefficients within the network, I'll get different answers if I look at these different parameters. So this leads to this difficulty of capturing from the parameters themselves the important characteristic. For example, if you want to prune out by removing small coefficients, by setting to 0 small coefficients, how do you know that they are really insignificant? So, as an example, let's look at the question of figuring out bounds on the Lipschitz constant of the function implemented by the network. And here, let's start by a simple multi-layer perceptron. So written as a composition of weight matrices and activations. If we focus on the ReLU activation function, which is known to be 1 Lipschitz, it's not difficult to show that the Lipschitz constant with appropriate metrics of your function is bounded by the product of the operator norms of your matrices. But this is not, well, an advantage is that this is relatively easy to compute. But as shown by my choice of colors, first of all, it's not sharp because if you rescale your matrices, the function doesn't change, but the bound can change. So clearly, some of the bound can be perhaps sharp for certain choices of rescaling, but not for other ones. And the lack of rescaling invariance make it even worse. The bound can be arbitrarily bad. It can be, it can blow up to infinity, while the Lipschitz constant of your function is finite. So if we note, let's denote this. This is just the product of norms. Well, of course, a simple way, mathematically speaking, to define a better bound is to consider the infimum of all possible rescaling, rescaled version of parameters. But now this raises another question, which is, first, is this bound sharp, but also probably how do you compute it? Here there's an infimum. And this is, we'll see in a few minutes that there are some answers to this question. So I focus here on the Lipschitz on the Lipschitz property, but more generally, if you want to compute distances between functions, again, or well, this Lipschitz constant, they are not easily related to direct properties of norms on the parameters, and so the overall purpose of this talk is to shed a light on the possibility to lift the parameters to representation, another finite dimensional space, which will be mathematically more convenient to work with, and which will capture the rescaling invariances in a way that enables to indeed capture distances and bound interesting properties in terms of properties of this lifting itself. So to consider such lifting, maybe it's worth starting with a few simple examples. So the simplest example I could think of is a neural network with one input, one hidden neuron, which is linear, and a single output. So there are two parameters, u and v, the weights of the two edges on the computational graph. And here, if you think of what it means to rescale these parameters, it just means to move along this hyperbola. If you start for some parameter, you can get arbitrary rescalings here. And here, since we're looking at the notion of lifting that that we are looking for is a notion of an invariant representation. Here, there's an easy invariant representation of the whole equivalence class, which is simply the product of the parameters, which is the equation defining this hyperbola. Of course, well, for practical applications, we're not going to be so much interested in such a simple network. So let's make things a bit more closer to reality. The first one is the second example is the case of a multilinear network. So again, more mathematical tool for analysis than something actually useful in practice. But in such a case, it's not difficult to see that the function is completely characterized what you know the product of the matrices. So there is indeed a lifting, a natural lifting of the parameter representation, which consists in computing the product of all the weight matrices and gathering all the entries of the resulting matrix in a single vector. Perhaps closer to something that becomes interesting here is the shallow neural network with the ReLU activation function. And here we need a few more steps to see how a lifted representation that is a rescaling invariant pops up. So such a network, in such a network, the parameters are, there's a number of neurons indexed by I, and for each neuron, there are incoming weights, outgoing weights. Incoming, outgoing. So this is the expression of the function it implements. But if you look at the ReLU activation function, you know it's zero in a certain regime, and it is passing. It's linear in the other regime. So you can rewrite this as a scalar which is 0 or 1, depending on properties of your inputs, times this inner product. So overall, you can write your function as a linear combination of here what we call activations, the activation of the neurons, binary valued, which are locally constant if you move x, except if you're not on one of the boundaries where the activation changes. And here, something that is expressed in terms of the outer product of your weights. So if you collect in a single matrix, or if you collect all these outer products, you get a representation of your weights. There is a rescaling invariant, which is finite dimensional. So you have a lifted version or representation of your parameters. Okay. Do you want to go to 3 layers, 4 layers? Maybe not, but we want to be able to represent more than 2-layer networks. In fact, Okay, so before we go there, what are the important properties that we'll try to capture in the more general context? Is that when in both of these cases, what we obtain is a lifting phi of theta, which lives in a finite dimensional space, such that locally around some parameters or around some input vector, we can factorize the function implemented by a network in terms of something that depends only on the lifting and the input of the network. And this, if you look closely in the eyes at the expression, everything is linear in X and linear in the lifting. So something that looks a bit like kernel representation where we linearize, but here there's a different role played by the lifting on the one hand and the input vector on the other hand. When I say linear in X, it's actually affine in X in more generality. So, but of course, we want to deal with more complex networks, that include convolution, pooling, skip connections, and can we design something of the same type in such a context? Well, this is the objective of this next short presentation. So now we can think of a network as it's a directed acyclic graph of computation. This one is layered, but you could imagine skip connections. Some of the neurons are equipped with the ReLU. Some are equipped maybe with a max pooling operation. It takes the max of the incoming values. And so this is your, and the neurons may have biases. And now in this type of graph, what you have is a number of paths. Some paths starting from an input neuron, going to to an output neuron, and some are starting from a hidden neuron. So for each of these paths, we'll define a value. We'll define a value which is the product, simply the product of the weights along the path. And so for neurons with biases, you have to multiply by the input bias. Similarly, on each path, you can also define an activation. Essentially, with paths with ReLU neurons, simply think of a path is activated if all the neurons are activated along the path. A single neuron being off kills the activation of the path. So so given a parameter, we can compute a value for each path. And we can compute, given a parameter and an input, we can compute an activation for each path. So what we can do is collect these into a vector. So the path lifting will be collecting all the values for all the paths, and the activation vector will be collect all the activations for all the paths. So you can imagine that you don't necessarily want to work with it in practice. The number of paths is high. We'll see a bit more on that later. But this is something you can conceive mathematically, and it is finite dimensional. So this is something that has some history. I mean, I think that the first reference I saw on this notion of path lifting dates from the work of Nechaber in 2015. It was dedicated to networks essentially with a single scalar output and ReLU activations, and and recently with Antoine, what we showed is that you can work with an arbitrary DAG and include max pooling and variance in the framework. Okay, this tells you how to build the path lifting, but what are the? I mean, why would you care? How can we use this path lifting? It has some important, some key properties. I think that the key ones are really summarized here, and I'll try to illustrate in a few minutes how they can be used to derive simple computations. The first one is that it really captures rescaling invariance. It's not difficult to show that if you have rescaling invariant parameters, they lead to the same lifted representation. They must also have the same sign. And if you have both equality of the lifted representation and the same signs, then indeed the network parameters are rescaling equivalent. But perhaps more important is this linearization property. So here, let's think for simplicity. Let's think of this representation for a scalar valued output. So here you really have an inner product between the path the path lifting vector and a vector that's the product of your input vector concatenated with one, so that you will be affine. You'll have an affine dependency on the input vector, and here a binary matrix that captures the activation of each path and essentially relates each entry of the network to some each path, I would say, to the corresponding entry. So this expression, in this expression, we can see several things. First thing, the locally affine dependency with respect to x, because this is a function that is binary and locally constant. So this recovers the continuous and piecewise linear behavior of the function. So this path activation, it will be very useful to know that it is, to know its structure. I'll come back to it. And this one, this is a polynomial lifting, since it's made of products along path. But once you've once you've made this product, the dependency on the parameters, on the lifted parameters, is becoming linear, and this will be convenient. Okay, so compared to my previous picture, now we have a rescaling invariant parameters. Not only are the functions that implement the same, but the lifted parameters the lifted versions of the parameters are equal, and this will enable the derivation of some bounds. Sorry. Some concrete techniques that can allow to prune networks in a rescaling invariant manner, and also to compute Lipschitz bounds in a rescaling invariant manner. Here is the hidden other application that I'm not going to talk about during this talk. And if time allows, I will also mention a few applications of the lifted representation to analyze the dynamics of when training such networks. Okay, so I hope you memorize somehow this linearization property. It will reappear anyway, so if you didn't have time to memorize it. But this is something that will be handy to manipulate the networks and prove bounds on. So, and here it is again. The idea is that it's possible to use such a representation to have a few lines proof of a bound, of a Lipschitz bound on a neural network. So the output, if the output is written like this, and here for just as a shorthand, I write x bar for the x vector concatenated with 1. The question is, we would like to bound the Lipschitz, have a Lipschitz bound on this function. Essentially, as you can imagine, we'll want to control some norms of the gradient of the function. For simplicity, we're looking at the scalar valued case. The first observation is that, we write it as an inner product and use a joint property. And here I simplify the notation because, we'll consider things locally, and this function is binary, this matrix is binary and locally constant, independent of the parameters and of the input vector. Now, so the local Lipschitz constant of my function is just the L1 norm of these gradients, but the gradient is precisely here. So, here there's a dependent. This is not the gradient. This is an extended version that takes into account the biases. So this is a valid bound on the Lipschitz local Lipschitz constant. Now, if I use simple algebra, it's just the definition of operator norms to get such a bound. And if you look at the particular structure of this matrix, it's binary valued. It has only one non-zero entry on rows or columns. I mean, whichever is needed here. So this operator norm is 1. As a consequence, you get a bound on the Lipschitz bound, which is just the L1 norm of this path lifting. This is something that was already observed in the work of Neishabur. This can be used to bound the Lipschitz property of the corresponding function. So overall, I mean, by taking the supremum over all x, you do have that this Lipschitz this Lipschitz bound, and the derivation in Neishabur is done by writing explicitly sums over paths everywhere. Here, simply by using this compact expression of the linearization property, it becomes a few lines. Okay, so to summarize, and this is valid for general. I mean, this is valid for general DAGs. We have this Lipschitz behavior with respect to input vectors, which is to be compared with the classical bounds written as a product of operator norms. And in fact, it can be shown that this reaches the infimum over all possible rescalings of this operator norm. So this is the sharpest bound of this type that can be obtained via rescaling. I'd just like to mention briefly that maybe if you wonder why we are maybe interested in Lipschitz, in controlling the Lipschitz constant, one reason is for robustness, to control the robustness of neural networks. Another one is that it also has consequences in terms of statistical generalization bounds, and it's possible to establish generalization bounds that exploit, again, the same L1 norm of the path lifting. Something that we can, another type of Lipschitz property that can be interesting is, in particular, when we quantize or prune networks where we replace parameters by other parameters, is the Lipschitz behavior with respect to the parameters themselves. And here, in a work that was just accepted through ICML this year, we can show that again, there's a Lipschitz bound in terms of the behavior, the distance in the Lipschitz space. So the distance between the function evaluation is bounded by the L infinity norm here, times the distance in the Lipschitz space. We'll come back to it in a minute, but first of all, this has consequences. If you have an initial parameter, you want to replace it by a pruned one or by a quantized one, then this quantity may measure what the effect of your approximation. But you may also wonder when seeing this is a high-dimensional vector. I mean, this lives in the space of paths, and there are many paths. This one too. You don't necessarily want to compute these vectors and compute differences between these vectors in practice. So in terms of computation, the number of paths can actually be very, very high. This is a simple standard ResNet. We are really in the the dimension of statistical physics, the number of paths. Yeah. So computing this lifted representation would be completely intractable, but luckily they are very structured and they are deeply related to neural networks, so deeply related that it's actually possible to use the network structure to compute these norms. So the first, it's possible to observe that if you take the absolute value of all network parameters, and if you apply the corresponding network to an input made of ones, then by the linearization property, you have a certain equality. And looking at the resulting expressions, this yields exactly the design L1 norm. So computing this Lipschitz bound, this L1 norm, is just one forward pass on a network where you've taken the absolute values of the network. By the way, if you want to compute L2 norms or LP norms, just take the coefficients to the pth power, and again you get all the LP norms of all your lifted representation. Now, maybe a bit more complicated is this setting, because here you have a difference between two vectors. But luckily, again, under some assumptions that will be satisfied in practice, if you assume that there's an ordering between your two weight vectors, one of them has all of its entries smaller than the other ones, then indeed the L1 norm of the difference is the difference of the L1 norms. And just so one forward pass is not enough, but two forward passes is enough to compute this difference, this norm, this metric. And if you wonder whether this is a reasonable assumption, whenever you prune out a network, you have one network with certain parameters and some are set to 0, so the assumption is satisfied. And also if you quantize, provided that you have a floor quantization and no rounding to the upper the ceiling. How am I doing on time? It's here. Okay. My goal here is to give a short proof to illustrate again how this linearization property can be used to prove this second bound in this second Lipschitz bound relatively nicely. So to begin with, remember what we want to bound is the difference between the evaluation of two functions corresponding to theta and theta prime. The first observation is that if we are at a point and pairs of parameters where the activations of all paths are the same, the bound is essentially trivial because of this linearization property. You use the linearization property for one parameter for the other because the activations are the same. Well, this is the expression you get, and just as I did before, a bit of transposition, a bit of Hölder inequality, and using that this has an operator norm that is bounded by 1. Here is the bound that we're looking for. Now, what happens? Of course, it's not always the case that we have the same activation on the two the two vectors that we consider. First, a small technicality. It's simpler to work with non-zero with vectors that have only non-zero, strictly non-zero entries. But because of the continuity of the function, we can restrict to the case. If we prove it for non-zero vectors, we'll prove it in the limit when they may have some zero entries. And this allows us to define some interpolating curve between our pair of parameters. Here, it's essentially interpolated in a log domain. I mean, it's a linear interpolation in the log domain. And this is where we use the fact that both vectors. This is a Lipschitz bound for parameters with the same sign. So this truly interpolates between our pair of parameters, and it's also possible to show that each entry is monotonic, and that actually on each path, this value is monotonic. So now, the particular shape of this function also enables to show that, there's analyticity and there's a finite number of breakpoints. So along this curve that maps the two parameters, there will be a finite number of breakpoints such that between two breakpoints, the activation of all paths is constant. And there we're almost done. I mean, we'll look at the parameters that are associated to each of the breakpoints, decompose this sum using a triangular inequality, use the bound proved when we have a constant activation here, develop this sum. I mean, the L1 norm is the sum of a path. So here, this is the only way where we go down to the only step where we go down to the path, the level of a path. And now monotonicity of the functions makes it possible to rewrite this sum as actually the difference between the endpoints. And once we're there, the bound is established. Okay, so we have Lipschitz bounds, and I evoked it, but it can be used now for practical application. An application is pruning. So if you have a vector, you may want to determine which entries to set to 0. So the individual problem is okay. Should I replace the vector with the same vector with one entry set to 0? So this is denoted theta minus I if I is the ith entry. Now, using our bound, we know that the approximation error we get is bounded by this quantity here. Everything, so we define as a criterion this difference, but because the assumptions before are satisfied, we can write it as this type of difference. So it's possible to use this as a criterion, and it will be rescaling invariant. We're actually lucky. It's also possible. I mean, this would mean looping over all possible entries, replacing the network by a network where you've changed, you've set something to 0, computing these both with forward pass. This would be many forward passes, but actually it's possible to compute the whole set of criteria in one step using auto-differentiation with the expression given here. So auto-differentiation gives allows to compute this criterion, and when testing it on off-the-shelf networks, it gives performance that is on par with standard iterative magnitude pruning. But in contrast to iterative magnitude pruning, this is fully rescaling invariant. So if an adversary changes the scale of your parameters, IMP will completely degrade, and this criterion will not be affected. Okay, I think I just have the time needed I just have the 10 minutes needed to say a few words about one last consequence or one last use of this listed representation, which is to study the dynamics of the training of neural networks by gradient flow. So just to set up the notation, we are in a learning framework. There's some loss, the individual loss. This is the global loss on a training set with certain training samples. And an observation is because we're considering some ReLU network with skip connections, DAX, max pooling, etc. As I said, locally, we can factorize the whole loss function in terms of some function of the lifted parameters. Here, the function captures, depends on the data set, depends on the loss, depends on all the labels, but there's a factorization where the dependency in the parameters is factored out through this lifted. So the dependency is factored out through the lifted parameters. So you're certainly familiar with gradient flow, which is the ideal, the small step idealization of a gradient descent. So if you consider the trajectory of parameters subject to this ODE, the gradient flow ODE, a natural question is to consider what is the trajectory of the lifted parameters. Apply the lifting to the parameters. By the way, before I get there, some of you I know are familiar with the notion of functions that are conservation laws during the trajectory. When you train parameters, because of the invariances it is known that some functions of the parameters remain constant along the trajectory. So whatever was the value at initialization, it remains, it's preserved all along the trajectory. So this captures some effect of initialization that cannot be escaped during the dynamics of the trajectory. This is something that can be captured through properties of the lifting, but this is not my main objective here. Here, what I would like to look at is something that is used in the analysis of the implicit bias of the training dynamics very often, is to try to look at the dynamics of these parameters. Via the chain rule, it's not difficult to show that the time derivative of the lifted parameters can be written in such a way. And here appears a matrix that's a priori defined in terms of the parameters, but not of the lifted parameters. So here we get a dynamics which is z dot equals minus m of theta times the gradient. If we had instead the possibility to write this as a function of the lifted parameters, then this would be a natural, naturally written dynamics in a Riemannian metric on the lifted parameters. So the question here is it possible? There are known cases where it's possible, but how can we, to what extent is it valid? So a quick summary of existing results. It is known, and Holger is somewhere here, I think, has worked on the topic. It is known that if you consider linear networks, deep linear networks, and you consider the lifting, which is the product of the weight matrices, then for certain initializations, the so-called balanced initializations, there's indeed a possibility to rewrite as a good, an intrinsic dynamics, an intrinsic Riemannian dynamics of this type. And as far as I know, it was only known or established for the balance conditions. And in fact, it's possible to extend this to quasi-balance conditions, which are conditions where it's not valid for arbitrary initial conditions. First, if you have there are initial conditions for which it will be impossible to rewrite things this way. But there's a slightly larger class of initializations that we call quasi-balance, on which the property remains valid. And second extension is now, if you look at general DAG ReLU networks, as I evoked them, then, and if you consider the lifted parameters using the corresponding ReLU lifting, then this can always be written as a proper intrinsic dynamics. Which means, in particular, that if you look at, linear networks, there are two ways to lift them. You can lift them with this sort of natural lifting for the linear case, but you could also lift them with there are a particular case of ReLU, deep ReLU networks. So you could also lift them with this other lifting. So the dynamics would be intrinsic there, but not necessarily intrinsic with respect to this lifting. So here is the not 3 lines, but 3 theorem proof of this fact. The first is something that we established with Sibyl and Gabriel in 2 years ago. So there's a notion of conservation laws, functions that are preserved, here vector valued functions that are preserved along the trajectory of for any training set, so the gradient flow trajectory. And now consider a function that concatenates these conservation laws, this maximal set of conservation laws, and the lifted representation. When this function is locally invertible, it is possible to rewrite this kernel metric as something implicit, depending only on the lifted parameters. And the proof is quite short. It's because along the trajectory, the first component remains constant. And because of local invertibility, you can write your parameters as a function only of these characteristics of the initial the conditions and of the current lifted parameters. And okay, and then you look at the expression. I mean, okay, this only depends on z and theta 0. The second, so once this is from 2 years ago. Now it was also established in the same paper that showing that this local invertibility is possible using some Lie algebra properties. We're using the so-called Frobenius property of the lifting. So you look just at the lifting, you do some computation, check some Lie algebra properties. If it has the Frobenius property, then we can apply the first theorem. And the new result from this year is that if you actually do the proper Lie algebra computation for the lifting associated to the ReLU networks, it always satisfies the Frobenius property, so the dynamics can be written intrinsically. Okay, I think it's the time in the 2 minutes, the 2 remaining minutes to conclude. So what I hope that I conveyed today is that okay, there's this notion of rescaling ambiguity or symmetry in the parameterization that a priori it's a problem if you want to capture information intrinsic to the corresponding function based on the only knowledge of the parameters, looking at the natural representation of parameters. But via the path lifting, you do have a rescaling invariant representation, and this leads to a number of concrete mathematical and practical application, including Lipschitz bounds. Something that I would not have time to mention, but using the lifting, it's also possible to characterize the convexity of neural networks and to design regularizers to promote networks that have that implement a convex function without necessarily being the so-called input convex neural networks. And finally, something that is not necessarily rescaling invariant but exploits the lifting is this analysis of the training dynamics. And so I also hope to have convinced you from the few derivations that it is, once you have the linearization property, it's relatively convenient as a mathematical tool, and that even from a computational perspective, even though the lifting itself is of combinatorial dimension, many of its the interesting quantities related to the lifting can actually be efficiently computed. If you want to play with it, there's an open source toolbox available here. Something, if we, to be complete, in terms of rescaling invariance, there are some properties. Rescaling invariance is not only a curse that can be harnessed, it's also sometimes a blessing. And if you're interested offline, I can say a few words about the fact that to quantize neural networks, it's possible to exploit the diversity of rescaling that are available to get much beyond the quantization, the performance of natural rounding for the same with so fewer bits for the same precision. And now, in terms of where to go next, now that we understand better via lifting the existing dynamic, it's quite tempting to understand to what extent invariant training could be designed and that naturally exploit the geometry in the lifted space. And my last word, although I was trying to convince you that there are there's much progress with the Lipschitz bound that we have established, etc. If you look at it carefully, in many places this remains very worst case analysis. They are the mixture of mixing lifting with all the natural randomness that occurs in the training of neural network is something where we expect that it's possible to go much beyond the worst case, but this is quite challenging. Thank you.
Yeah, thanks for the talk. So, you looked at ReLU and linear, right? But there are quite many other, activation functions that have invariances, and people have looked at that, in particular for the training dynamics, and applying Noether's theorem, which essentially, what you do to get the conserved quantities, right? To observe that you get conserved quantities, and that in the gradient flow gives you particular paths, right? Now, so what's not clear to me is what was observed is that if even in the linear system and so on, it's not, it makes a difference that you have many of them, and they don't behave the same, and there can actually be quite some advantage of over parameterizing in that sense, and that's true also in other things, even though it's actually silly to do because all the linear ones are the same. So it's not clear to me whether or not through your lifting you don't take out the very thing that makes it actually useful.
Okay, so thanks for the question. So first, for the moment, I wouldn't say that I use the lifting to change the way we train, because you particularly mentioned that redundancy, over-parameterization has positive effects. If you, most of the time that I spent on the lifting was on using it as a mathematical analysis tool rather than a tool to design new optimization algorithms. This is more the last question that I ask. Can we use now? Could we use it for invariant training? And here is my viewpoint. I completely agree that we don't really know what makes things so successful but there's the over-parameterized training, but there's the intuition that being over-parameterized probably gives more the freedom in navigating between in the landscape. Yet, much of the analysis that is done to understand and to prove the convergence of the schemes under certain conditions exploits conservation laws, exploits them to understand the associated implicit bias, and somehow now that we know that this implicit bias is helpful. The solution that we find in practice, if they satisfy this implicit bias and they seem to perform well, there remains the question that I believe is quite natural: is can we go more straightforwardly, more directly to the same type of implicit bias, but by navigating in the right in a domain that is more intrinsic. To me, it's still something disturbing to think that if you start from two different parameters that are completely independent, that cannot be distinguished from a functional perspective, that they can lead to completely different outcomes of the training process.
But that's what I mean. I think that's the essence. That's actually important that you have that they have this thing. That's what I mean. I think it's actually important that they lead to different things. That's the essence. And I think if you take that out, you will miss that. But maybe we take this offline.
Okay. I think I have a slightly more low-level question. So you mentioned the balancedness condition when dealing with the linear networks. So for example, if you have a linear network and you train with gradient descent, then you do converge to a balanced solution. So does this mean something for your analysis?
So there's an ingredient in what you're saying. So you're saying that if you train a linear network, you converge to a balanced solution if you use weight decay.
Yeah.
Yeah, it's.
So does that mean something for your analysis?
So that means something. First of all, as soon as you put weight decay, it means that you use a regularizer in your descent method, and this regularizer depends on the parameters in a way that cannot be factored via lifting. So you have a training that is not rescaling that cannot that has that breaks rescaling invariance.
Yeah, this I understand, but some of your results are
but there's
static.
also a few more things. It's first. Okay. I tend to think a lot in terms of conservation laws. There are conservation laws in a generalized sense with weight decay, and these conservation laws are directly related with the ones without weight decay. So the fact that you end up in a point where where everything is balanced. You can even capture the speed at which it converges to this balancedness. So yes, in these balancedness conditions, they are related to these final balancedness conditions. They bear some relation with the lifting. But I'm not sure this is the nature of the question you had.
Yeah, what I wanted to understand is, so it seems to me that you're also partly a static analysis in the sense that if your network is balanced, then your bounds will tell you something about the structure, say, of the Lipschitz constant or stuff like that. So what I'm saying is, say, even if you take actually a nonlinear network, so take a deep network where you have a bunch of nonlinear layers and then you have a final linear head, and train that with L2 plus weight decay, then what happens is that the final linear head also becomes balanced.
Absolutely,
You can also show that. So I'm wondering if that has any consequence on the type of analysis that you do, because now you know that the part of it is balanced, so maybe that helps extract meaning from the type of calculations that you do afterwards. This was my question.
So there are two types of calculations. I mean, I talk about at the very end. I talked about the dynamics. So this is really dynamic.
Let's say something about the statics.
But indeed, the Lipschitz properties that I looked at are static. I mean, you give me a pre-trained network, and I looked at its properties. And this is precisely. I would relate it this to your question to this notion of beyond worst case that I mentioned to begin with. I mean, the worst case. The bounds I established. They are tight in a sense. I mean, I can find networks that have, if I put all the weights to be positive, the bounds are tight. But neural networks that you train, they don't have all weights non-negative. Typically, they start from random weights, and there's also a sort of preservation of. There's the drift from initial random weights to the final weights. Typically does not align all the signs. This dynamics is probably important to understand a regime or a training time during which you can have much better, much sharper bounds that control the actual behavior of your trained network.
Thanks.
Any more questions? No? Okay. Then let's thank Remy once again. And yeah, this concludes our session. I guess, Helmut, you got some announcements to make.
Okay.
Okay.
Thank you very much. So we are done for today. For those of you who would like to walk from the hotel to the banquet, it's about 40 minutes walking according to Google Maps. So I would suggest that we meet at 6 o'clock in the lobby or just outside the hotel, and then we can all walk together. Otherwise, well, I look forward to seeing all of you at 7 o'clock at the dinner. Thank you.
Could you remind us of the precise address?
I sent it in an email, but I'll be happy to. Yeah, it's Hôtel du Louvre.
Next to the pyramid.
Yeah, next to the Louvre. So, but I can email it again now. I don't. I mean, I have to look it up. Yeah, I can look it up now. I don't know. Yeah, I'll tell you. Yeah. Good. Thank you.